You are given 8 identical looking balls. One of them is heavier than the rest of the 7. All the others weigh exactly the same. You are provided with a simple mechanical balance and you are restricted to only 2 uses. Can you find the heavier ball? Let me repeat the puzzle. You are given 8 identical looking balls. One of them is heavier than the rest of the 7. All the others weigh exactly the same. You are provided with a simple mechanical balance and you are restricted to only 2 uses. Can you find the heavier ball by using only 2 uses of the mechanical balance? Let me explain the solution now. For convenience sake, let's name the balls 1 to 8. First, we weigh 1, 2, 3 on the left and 4, 5, 6 on the right. This is the first measurement. There are 3 scenarios which can arise from this. Let's consider the scenario 1. If the left side is heavier, then we know that one of 1, 2 or 3 is the heavier ball. Now in the second measurement, weigh 1 on the left and 2 on the right. We will know if 1 or 2 is heavier. If they balance out, then 3 is the heavier one. Thus, heavier ball is identified by exactly 2 measurements in this scenario. Let's consider the scenario 2. If the right side is heavier, then we know that either 4, 5 or 6 is the heavier ball. Now in the second measurement, weigh 4 on the left and 5 on the right. By doing this, we will know if 4 or 5 is heavier. If they balance out, then 6 is the heavier one. Thus, heavier ball is identified by exactly 2 measurements in the scenario 2. Let's consider the final scenario, that is scenario 3. If 1, 2, 3 and 4, 5, 6 balance out, then we know either 7 or 8 is the heavier one. Weigh both of them to find out which one is heavier. Again here, heavier ball is identified by exactly 2 measurements. Let me summarize. The first step is determining which set of 3 balls contains the heavier one. So choose balls 1, 2, 3 and balls 4, 5, 6 and weigh them. If one set is heavier, save those 3 balls. Pick 2 balls and place for measurement. By doing this, we will know which one is heavier. If they balance out, then other is the heavier one. If neither side is heavier in the first step, proceed with balls 7 and 8. In the final weighing, weigh both of them to find out which one is heavier. By following these simple steps, we can find which ball is heavier in just 2 measurements. The scenario comprises of a wobbly bridge and 4 people. It is the night time and the people have only 1 torch. Without torch, one may risk his life in crossing the bridge. Also, we have a condition. The bridge is not quite strong and can hold only 2 persons together at once. The 4 people take different time to cross the bridge. The timings are 1 minute, 2 minutes, 7 minutes and 10 minutes. Since the torch is a necessity and the bridge can't hold more than 2 persons at a time, 2 persons must travel at a time, out of which one must return with the torch so they don't risk their life crossing in the dark. What is the shortest time that will be required for all of them to cross the bridge? Let me simplify the puzzle. 4 people need to cross a bridge at night. Unfortunately, they have only 1 torch and the bridge is too dangerous to cross without one. The bridge is only strong enough to support 2 people at a time. Not all people take the same time to cross the bridge. Times for each person is 1 minute, 2 minutes, 7 minutes and 10 minutes. For example, if the 2 people with the speed 7 and 10 minutes were to cross together, it would take 10 minutes, leaving 17 minutes for one of them to return and get the rest moving. Can you find what is the shortest time needed for all 4 of them to cross the bridge? Were you thinking of using the fastest person who takes 1 minute to travel to and fro till everyone has reached the other end? Yes, that can be done, but it will take 10 plus 1 plus 7 plus 1 plus 2 equals 21 minutes in total. If you pay attention towards finding a way to merge the one taking 7 minutes and the one taking 10 minutes, we will have to acknowledge the fact that one of them will also have to return back, which will take much more time than 21 minutes. What if we use the person taking 2 minutes to escort the one taking 1 minute across? Let's come to the conclusion. So in first step, 192 crosses the bridge and 2 returns with the torch. Here time taken is 2 plus 2 equals 4. In the second step, 7 and 10 crosses the bridge and one who was already in the other side come back. Here time taken is 10 plus 1 equals 11. In the final step, 192 crosses the bridge. Here time taken is 2 minutes. In such a manner, the total time taken will be 2 plus 2 plus 10 plus 1 plus 2 equals 17 minutes. Alternatively, the same time can be achieved like this. 1 and 2 go first, then 1 comes back, then 7 and 10 goes and 2 comes back, then 1 and 2 go again. It makes a total of 17 minutes. You are a king of an empire. You have a servant working in your palace. He works all the 7 days and you only pay him in the form of gold bar. You must pay the worker for his work every day at the end of the day. If you are only able to make 2 breaks in the gold bar, how will you pay the servant if the servant works for the equal time every day and thus equal amount must be paid at the end of the day? If you are thinking of how to cut in such a way that you are able to make 7 equal pieces, you are thinking in the wrong direction. You should give more stress on how to make the transactions with the worker. So the trick is not to try and how to cut in such a way to make 7 equal pieces, but rather to make transactions with the worker. Make 2 cuts on the gold bar such that you have the following sizes of bars. Bar A should be 1/7 of the bar, bar B should be 2/7 of the bar, bar C should be 4/7 of the bar. Let's check whether it is going to work. When the day 1 ends, give bar A to the worker. Here you remain with bar B and bar C. Worker possesses bar A. When the day 2 ends, give bar B to the worker and take the bar A back. Here you remain with bar A and bar C. Worker possesses bar B. When the day 3 ends, give bar A to the worker. You remain with bar C. Worker possesses bar A and bar B. When the day 4 ends, give bar C to the worker and take back bar A and bar B. Here you remain with bar A and bar B. Worker possesses bar C. When the day 5 ends, give bar A to the worker. You remain with bar B. Worker possesses bar A and bar C. When the day 6 ends, give bar B to the worker and take back bar A. Here you remain with bar A. Worker possesses bar B and bar C. When the day 7 ends, give bar A to the worker. Here you remain with no bar. Worker possesses bar A, bar B and bar C. Thus by the end of 7 days, you have taken care of everything. There is an equilateral triangle and 3 bugs are sitting on the 3 corners of the triangle. Each of the bugs picks up a random direction and starts walking along the edge of the equilateral triangle. What is the probability that none of the bugs crash into each other? Here in this puzzle, every bug has 2 choices. Pick either of 2 edges, go through the corner on which bug is initially sitting. If you have come up with the fact that the bugs can avoid the collision only when they decide to move in the same direction, be it clockwise or anti-clockwise, you have already solved half of it. In any other way, the bugs will definitely run into each other. Now the bugs can move either clockwise or anti-clockwise. The probability of choosing a specific direction is then 1 over 2. We will utilize the simple equation of probability to find out our answer. The probability of no collision equals probability of the bugs move in clockwise direction plus probability of the bugs move in anti-clockwise direction. Probability of the bugs move in clockwise direction is 0.5 times 0.5 times 0.5. This is because there are 3 bugs and each bug have 2 options, either moving in clockwise or anti-clockwise direction. Similarly, the probability of the bugs move in anti-clockwise direction is 0.5 times 0.5 times 0.5. This is because there are 3 bugs and each bug have 2 options, either moving in clockwise or anti-clockwise direction. Hence, probability of no collision equals 0.5 times 0.5 times 0.5 plus 0.5 times 0.5 times 0.5, which is equal to 0.25. Thus, the probability that the bugs won't collide into each other is 0.25 or 1 over 4 or 1/4. Suppose you have a regular hexagon made up of matchsticks with 3 diagonals in it. The task is to convert the given hexagon into 3 equilateral triangles by moving only 4 matchsticks. Before actually getting into the problem, let me explain what are hexagon and equilateral triangle. A hexagon is a 6-sided 2-dimensional geometrical figure. The total of the internal angles of any hexagon is 720 degrees. A regular hexagon has 6 rotational symmetries and 6 reflection symmetries. All internal angles are 120 degrees. An equilateral triangle is a triangle in which all 3 sides and angles are equal. All 3 internal angles of equilateral triangle measure 60 degrees. Let's get into the puzzle now. Here is a regular hexagon made up of matchsticks with 3 diagonals in it. The task is to convert the given hexagon into 3 equilateral triangles by moving only 4 matchsticks. Let me explain the solution now. Solution can be achieved by moving 2, 4, 5, 6 numbered matches to get exactly 3 equilateral triangles. First, move matchstick 4 adjacent to matchstick 7. Next, move matchstick 6 adjacent to matchstick 8. Next, move matchstick 5 and connect to matchstick 6, and it forms the base for the part of the triangle 3. Finally, move matchstick 2 and connect to matchstick 4 and 5, which forms the complete base for the triangle 3. Now we can clearly see that there are 3 equilateral triangles. 2 triangles are formed with side equals single matchstick, whereas third triangle formed with sides 2 matchsticks. A farmer lives on a small plot of land next to a river. One day he travels across the river in a small boat and purchases a fox, a chicken and a bag of corn from a feed and supply store. When the farmer returns to his boat to cross the river again and go home, he realizes he has a problem. The farmer can only take one item in his small boat at a time, otherwise he risks capsizing. He cannot leave the fox alone with the chicken because the fox will eat the chicken. He cannot leave the chicken alone with the corn because the chicken will eat the corn. How does farmer will cross the river without losing anything? A farmer lives on a small plot of land next to a river. One day he travels across the river in a small boat and purchases a fox, a chicken and a bag of corn from a feed and supply store. When the farmer returns to his boat to cross the river again and go home, he realizes he has a problem. The farmer can only take one item in his small boat at a time, otherwise he risks capsizing. He cannot leave the fox alone with the chicken because the fox will eat the chicken. He cannot leave the chicken alone with the corn because the chicken will eat the corn. How does farmer will cross the river without losing anything? First, the farmer must take the chicken across the river, leaving the fox and corn alone together on the starting side. This is a good move because fox will not eat corn. Then the farmer goes back and gets the fox. When he takes the fox across the river to the other side, instead of leaving the fox alone with the chicken, he swaps them out and takes the chicken back to the starting side. In the starting side, he then swaps the chicken out for the corn and brings it across, leaving the fox and corn alone on the far side. Finally, he goes back to get the chicken, bringing all three items across the river to the far side without letting anything eat anything else. By following this simple logical approach, farmer brought all three across river without losing anyone. You have 10 boxes that contains balls with each of the ball weighing 10 grams precisely. Now among the boxes, one of the box comprises of defective balls with each defective ball weighing 9 grams. You have been provided with an electronic weighing machine, but you are allowed to use it only once. Can you find the box with the defective balls? The puzzle looks difficult, but by the time you understand the solution, you will find that it was way easy than you were thinking. For convenience sake, let's name the boxes from 1 to 10. In order to solve this problem, you have to leverage the fact that you know exactly what each good ball is supposed to weigh and what each defective ball is supposed to weigh. Many of us instinctively will take one ball out of each box and try to find a way to make it work, but the trick is to take different number of balls from each box. The number of balls you pick from each bag is equal to the box number. For example, pick one ball from box 1, two balls from box 2, three balls from box 3, and so on, and finally 10 balls from box 10. In total, you will have 55 balls. If all of the boxes have good balls, then the total weight of these balls would be 1 plus 2 plus 3 plus till plus 10 times 10, which is equal to 550 grams. This is because each ball weighs 10 grams. 550 grams is not possible because we are already told in the puzzle description one of the box comprises of defective balls with each defective ball weighing 9 grams. So this is the catch to solve this puzzle. If box 1 has defective balls, then the total weight should be 1 gram less than expected. It is because only one ball weighing 9 grams. If box 2 has defective balls, then the total weight should be 2 grams less than expected. It is because 2 balls weighing 9 grams. Similarly, if box 3 has defective balls, then the total weight should be 3 grams less than expected. It is because 3 balls weighing 9 grams. So once you weigh the set of chosen balls, find out the difference between the total weight and the expected weight. That number represents the box number which contains the defective balls. By following these simple steps, we can solve this puzzle and defective box can be identified with single weigh. Two trains are on same track and they are coming toward each other. The speed of first train is 50 km per hour and speed of second train is 70 km per hour. A bee starts flying between the trains when the distance between two trains is 100 km. The bee first flies from first train to second train. Once it reaches the second train, it immediately flies back to the first train, and so on until trains collide. We are supposed to calculate the total distance traveled by the bee given that speed of bee is 80 km per hour. Let me explain the solution now. Let us make some assumptions first. Let the first train A move at u kilometers per hour. Let the second train B moves at v kilometers per hour. Let the distance between two trains be d kilometers, and let the speed of B be b kilometers per hour. In order to solve this particular puzzle, it is important to understand what is speed. Speed tells us how fast something or someone is traveling. You can find the average speed of an object if you know the distance traveled and the time it took. The formula for speed is speed equals distance divided by time. To work out what the units are for speed, you need to know the units for distance and time. In this puzzle, distance is in kilometers and time is in hours. So the units will be in kilometers per hour. The formula speed equals distance divided by time can be rearranged just like any other equation. The formula can be rearranged in three ways. In order to calculate speed, the formula becomes speed equals distance divided by time. To find distance, distance equals speed multiplied with time. To calculate time, time equals distance divided by speed. To calculate one of the variables, speed, distance or time, we need the other two. Therefore, the time taken by trains to collide in this puzzle equals distance divided by speed. Here distance is d and speed is sum of speed of train A and train B, which is u plus v. Hence time taken by trains to collide equals d divided by u plus v. Now putting all the known values into the above equation, we get, so we know that u equals 50 kilometers per hour, v equals 70 kilometers per hour, d equals 100 kilometers and b equals 80 kilometers per hour. Therefore the total distance traveled by B, that is distance, equals speed multiplied with time. We know that speed of B is 80 kilometers per hour and total time B travels is d divided by u plus v. After substituting, the equation becomes distance equals B multiplied with d divided by u plus v. Substituting the values of B, d, u and v, equation becomes 80 times 100 divided by 50 plus 70. After solving, it results in approximately 66.67 kilometers. Thus total distance traveled by B is 66.67 kilometers. I am sharing one more similar puzzle. Try to solve this by yourself before checking the solution. Puzzle states that there are two trains, say train A and train B, running on the same track towards each other at a speed of 100 kilometers per hour. They enter a tunnel 200 kilometers long at the same time. As soon as they enter, a supersonic bee flying at a rate of 1000 kilometers per hour also enters the tunnel from one side, say train A side. The bee flies towards the other train B, and as soon as it reaches the train B, it turns back and flies back to the train A. This way it keeps flying to and fro between the trains A and B. The trains collide after a certain point of time, leading to a massive explosion. The task is to find the total distance traveled by the bee until the collision occurred. Let me explain the solution now. This puzzle can be solved with the help of basic physics and observation. We know that speed of train A and train B equals 100 km per hour. Length of the tunnel equals 200 kilometers. Since both the trains are traveling at the same speed, hence they must have traveled equal distance before colliding, which means that they must have collided at the off way of the tunnel. Therefore, distance traveled by each train before colliding equals 100 kilometers, because the length of the tunnel is 200 kilometers. And time taken by each train to travel 100 kilometers and collide equals distance divided by speed, which is equal to 100 by 100, which is equal to 1 hour. Therefore, the bee must have traveled for 1 hour before colliding with the trains. Hence, distance traveled by the bee in 1 hour before colliding equals speed multiplied with time, which is equal to 1000 multiplied with 1, which is equal to 1000 kilometers. Thus, total distance traveled by bee until the collision occurred is 1000 kilometers. By following these simple steps, we can solve these kind of puzzles accurately in less time. Anand has 3 daughters. His friend Ravi wants to know the ages of his daughters. Anand gives him first hint. The first hint is the product of their ages is 72. Ravi says this is not enough information. Then Anand gives him a second hint. The second hint is the sum of their ages is equal to my house number. Ravi goes out and look at the house number and tells, I still do not have enough information to determine the ages. Anand admits that Ravi cannot guess with these hints, and then he gives him the third hint. The third hint is the oldest of the girls likes strawberry ice cream. Now Ravi able to guess after the third hint. Can you guess what are the ages of 3 daughters? So feel free to pause the video and try yourself before checking the solution. Let's check the solution now. To start with, list out all possibilities to get 72 from product of 3 different ages. Because the first clue given is that the product of 3 daughter ages is 72. So here are all possibilities to get 72 from product of 3 different ages. Since there are multiple possibilities, it is difficult to guess the ages of 3 daughters with this specific hint. Let's check the second hint now. The second hint is the sum of their ages is equal to my house number. So we have already possibilities of product of 3 daughters age. Here are sum of their ages. We have already calculated the product. Now let's see what are the sum of their respective ages. If you carefully observe in this particular detail, all sums are unique except 14. So the age sum must have been 14, otherwise Ravi would have guessed the ages from hint 2 itself. So we have 2 possible combinations to get sum 14, that is with 2 plus 6 plus 6 which is equal to 14 and 3 plus 3 plus 8 which is equal to 14. Since there are 2 possibilities, it is difficult to guess the ages of 3 daughters here also. So let's check the third clue now. So the third clue says that the oldest of the girls likes strawberry ice cream, which clearly says that Anand has an oldest girl and not 2. That means the oldest daughter cannot be of 2 numbers. Hence we can rule out 2 plus 6 is equal to 14 option, because oldest daughters are 2 in this case. So the ages must be 3, 3 and 8, and that's the solution. So ages of 3 daughters are 3, 3 and 8. One man has 81 cows. They give milk as per their numbers. Like 5th number cow gives 5 liters of milk. 10th number cow gives 10 liters of milk. The 81st number cow gives 81 liters of milk, and so on. That man has 9 sons and he want to give 9 cows each son and want each son get same liters of milk. So how he distribute those 81 cows to his sons? Let me simplify the puzzle. A man has 81 cows numbered 1, 2, 3 till 81. The beauty is that cow number 1 gives 1 liter of milk, cow number 2 gives 2 liters of milk, and so on. The man wants to equally distribute the cows among his 9 sons so that each one of them gets the same quantity of milk. So how he distribute those 81 cows to his sons? There are multiple solutions for this problem. In this video, I will explain the most appropriate way of solving this problem in steps. In the first step, let's find the total liters of milk from 81 cows, which is nothing but 1 plus, 2 plus, 3 plus and so on till plus 81. This is because as per the problem, each cow gives milk as per their number. Like the 5th number cow gives 5 liters of milk and the 10th number cow gives 10 liters of milk. The 81st number cow gives 81 liters of milk and so on. If you observe this series, this is sum of n natural numbers where n here is 81. We know that sum of n natural numbers can be calculated using the formula n times n plus 1 divided by 2. Here n is 81. Substituting the value of n in the equation becomes 81 times 81 plus 1 divided by 2, which is nothing but 81 times 82 divided by 2 equals 81 times 41, which is 3321. Thus total liters of milk from 81 cows is 3321. In the next step, find how much milk should each son get. So each son should get 3321 divided by 9, which is equal to 369. Thus each son should get 369 liters of milk. In the next step, write the full sequence from 1 to 81 in a straight line and then add the extreme numbers in pairs. So here the first extreme numbers are 1 plus 81, second extreme numbers are 2 plus 80, third extreme numbers are 3 plus 79 and so on. So each pair will add up to 82. 4 such pairs will add up to 328. So why we are doing this is we are trying to bring the numbers closer to 369 because each son should get 369 liters of milk. So let's give 4 such pairs to each son, so 8 cows to each son. Each of them will have 328 with them. The orders look like this. Son 1 will have the first 4 and the last 4 cows. Son 2 will have the next 4 cows from either end, and son 3 will have the next 4 cows from either end and so on. So after distributing the cows in this manner to all 9 sons, now there are 9 cows remaining, that is from 37 to 45. To get to 369, each of them need 41 more. So 41 is the 5th in sequence, so let's give 41 to the 5th son. Now he has 328 plus 41, which is equal to 369. He is sorted. Now there are other 8 sons which requires additional cow in order to satisfy the condition. Now consider the remaining sons in pairs. Son 1 and son 2 in pair, son 3 and son 4, son 6 and son 7, son 8 and son 9. First consider son 1 and son 2. If you give 37 to son 1, then he is 4 short. So swap a pair of cows between the 2 sons that has a difference of 4. So basically it is only 1 cow. So they swap their first cows. So the difference in the first cows will yield 4. After swap, so at this stage, son 1 have these following cows and son 2 have these following cows. So he needs a cow that covers for the 41. He was short in the first place and the 4 he gave to son 1. So the only option is 45. After giving cow with the number 45, this pair is sorted. So now take the next pair. Each of them are 41 short, but we only have cows which are plus or minus 3, plus or minus 2 and plus or minus 1 away from 41. So for this pair, let's do with plus or minus 3. So give 38 to son 3. It will now be 3 short. So swap a cow with a difference of 3. There are 6 possibilities. Let's go with 10 from son 3. A swap with 13 from son 4. Now son 3 is sorted and now the only option is 44 to son 4. So this pair is also sorted. For the next pair, there are again 41 short, but we only have cows which are plus or minus 2 and plus or minus 1 away from 41. If we do plus or minus 2 for this pair, then give 39 to son 6. It will now be 2 short. Swap a cow with son 7 with a difference of 2. So son 6 will now gain 2 and be equal to 369. Son 7 will now need to make up for the 41 he needed anyway and the 2 he lost to son 6. The only option is 43, so this pair is also sorted. For the final pair, we only have cows 40 and 42 remaining with plus or minus away from 41. Give 40 to son 8, he will now be 1 short. Swap a cow with son 9 with a difference of 1. So son 8 will now gain 1 and be equal to 369. Son 9 will now need to make up for the 41 he needed anyway and the 1 he lost to son 8. The only option is 42, so this pair is also sorted. Now all 9 sons have 9 cows and the total number of liters of milk each son will get 369 liters. As you can see here, in this method alone, there are many combinations possible. There is a bag of rice given to us and we need to get 1 kilogram of rice from it. But we have only a common balance with 2 pans, some vessels and a 1 gram weight. What is the least number of ways we need to carry out to get 1 kg of rice? Pause the video and think about the puzzle. Share your answer in the comment section. Let me explain the solution now. So there are 2 parts in the video. The first part, I will explain the solution to this particular puzzle. In the later part of the video, I will explain general solution for this puzzle. So in general, we need to follow these steps to obtain the solution. Let's name 2 pans A and B of the common balance and the 2 pans weigh equal in each way. Rice of certain weight obtained in a step is used in the next steps along to get rice of more weight. Assume that the left pan is A and the right pan is B. And in each ways, pan A contains certain reference weight and pan B is filled with enough rice from the bag to balance it. In some cases, pan B may have the 1 gram weight also in addition to the rice to be taken from the bag, while pan A may have just rice of some known weight. So the actual solution to this problem is we can get 1 kg rice in 10 ways. But how? Let me explain in steps now. So in the first way, put 1 gram weight in the pan A which is available with us versus 1 gram rice in the pan B. So here 1 gram rice obtained in the first way is moved to pan A. So in the second way, put 1 gram weight plus 1 gram rice in the pan A versus 2 gram rice in the pan B. Here the 2 gram rice obtained in the second way is combined with 1 gram rice existing in pan A for the next way. In the third way, put 1 gram weight plus 3 gram rice in the pan A versus 4 gram rice in the pan B. The 4 gram rice obtained in the third way is combined with 3 gram rice existing in pan A for the next way. In the fourth way, put 1 gram weight plus 7 gram rice in the pan A versus 8 gram rice in the pan B. So the 8 gram rice obtained in the fourth way is combined with 7 gram rice existing in pan A for the next way. So similarly in the fifth way, put 1 gram weight plus 15 gram rice in pan A versus 16 gram rice in pan B. The 16 gram rice obtained in the fifth way is combined with 15 gram rice existing in pan A for the next way. Now in the sixth way, put 1 gram weight plus 31 gram rice whichever was obtained in the pan A, so versus 32 gram rice in the pan B. So this is the most important step. See, all other steps remain constant, but this is the only step where it requires out of the box thinking. So here in this step, what we have to do is the 32 gram rice obtained in the sixth way and existing 31 gram rice in pan A are together put in pan A and 1 gram weight is put in pan B for the next way to get 62 gram rice from the bag. So this is the most important step. I will explain why we are going to do this particular step when I am giving the general solution. So now the 6 steps are over. Now in the 7th way, put 32 gram rice plus 31 gram rice in pan A versus 1 gram weight plus 62 gram rice in the pan B. So now here 63 gram rice in pan A and 62 gram rice in pan B are together put in pan A for the next way. So in the 8th weight, put 125 gram rice in pan A versus 125 gram rice in pan B. The total obtained rice will be 250 grams. From this step, we need not to use 1 gram weight. So here the 125 gram rice obtained in the 8th weigh is combined with the 125 gram rice existing in pan A for the next weigh. In the 9th, put 250 gram rice in the pan A versus 250 gram rice in the pan B. So the 250 gram rice obtained in the 9th weigh is combined with the 250 gram rice existing in pan A for the next weigh. In the 10th weigh, we have 500 gram rice in the pan A versus 500 gram rice in the pan B. Now combine both the contents of pan A and pan B to get 1 kg of rice. So by following these steps, we can get 1 kg rice in 10 ways. The most important step one must remember in this problem is the step 7. So now I will explain the general strategy. As we have only a 2 pan common balance and 1 gram weight to start off, we can only grow at a rate of 2 to the power of n. And to reach 1000 grams from 1 gram, we need at least 10 steps or 10 ways. Imagine a 3 pan balance. We can grow approximately tripling the weight of the rice. Similarly for an n pan balance where n is greater than 3. But if we reach 1024 grams, that is with 2 to the power of 10, we need to remove 24 grams of rice, which needs extra ways, which we are not interested in. So we realize that 1000 divided by 2 equals 500, 125 by 2 equals 62.5, and 62.5 divided by 2 equals 31.25, and so on. But what is important to notice here is the first small whole number in the above series is 125. That can be obtained by 63 plus 62, and we know we have a 1 gram weight, and hence when we go on approximately doubling the weight of rice, 1 gram weight plus 31 gram of rice versus 32 gram rice is obtained. Put this 32 gram in vessel V1 so to get 125 gram rice. We can weigh by keeping that 31 gram of rice in left pan A and get 31 gram rice in right pan B and keep the new 31 gram in a vessel V2. And again repeat the same to get 31 gram in pan B. Now combine pan A plus pan B plus vessel V1 plus vessel V2 to get 125 grams. If you observe in these previous ways, we are not doubling the rice we have, so the extra vessels are given in the question only to detract the problem solver. Precisely here lies the trick. If we don't grow double at any step, we are not going to achieve minimum ways to get 1 kg of rice. So we have to get to 125 gram quickly than this. One way, as you can contemplate, is to just double or approximately double in each step to get the minimum required ways. Hence, once 1 gram weight plus 31 gram of rice versus 32 gram rice is obtained, we double the rice approximately than what we have by keeping 63 gram in pan A and keep 1 gram weight in pan B, and thus get 62 gram of rice, which is 4 less than 63 into 2 grams. And then combine all the rice we actually have 125 gram rice which we needed in the first place. So from here we can double the rice and get 1 kg rice. So by following this logic, we can get the required result in simple steps. A team of 3 people decide on a strategy for playing the following game. Each player walks into a room. On the way in, a fair coin is tossed for each player, deciding that player's hat color either red or blue. Each player can see the hat colors of the other 2 players but cannot see his own hat color. After inspecting each other's hat colors, each player decides on a response, which are one of the following. I have a red hat, or I have a blue hat, or I pass. The players' responses are recorded, but the responses are not shared until every player has recorded his response. The team wins if at least one player responds with a color and every color response correctly describes the hat color of the player making the response. In other words, the team loses if either everyone responds with I pass or someone responds with a color that is different from his hat color. What strategy should one use to maximize the team's expected chance of winning? Let me repeat the puzzle. A team of 3 people decide on a strategy for playing the following game. Each player walks into a room. On the way in, a fair coin is tossed for each player, deciding the player's hat color either red or blue. Each player can see the hat colors of the other 2 players but cannot see his own hat color. After inspecting each other's hat colors, each player decides on a response which are one of the following. I have a red hat, or I have a blue hat, or I pass. The players' responses are recorded, but the responses are not shared until every player has recorded his response. The team wins if at least one player responds with a color and every color responds correctly describes the hat color of the player making the response. In other words, the team loses if either everyone responds with I pass or someone responds with a color that is different from his hat color. What strategy should one use to maximize the team's expected chance of winning? For example, one possible strategy is to single out one of the 3 players. This player will respond, I have a red hat, and the others will respond, I pass. The expected chance of winning with this strategy is 50%. Can you do better? A better solution exists for 75% chances of winning. Let me explain the solution in detail. Let the players be player A, player B, and player C. With 3 players and 2 hat colors, there are a total of 8 likely outcomes. Here are the outcomes. One special feature about the distribution is that most outcomes, that is 6 of them, include at least one hat of both colors. Here are the 6 outcomes which have at least one hat of both colors. As we can see here, in these 6 combinations, 3 combinations include 2 red color hats and other 3 combinations include 2 blue color hats. Only 2 extreme outcomes don't have at least one hat of both colors. Remaining are the ones with all red hats or all blue hats. We can analyze further. Among outcomes with both hat colors, there logically has to be 2 hats of one color. We call it as the majority color, and 1 hat of another color. We call it as the minority color. Here is the representation of majority and minority colors. Here in the outcomes, in first, second, and fourth combinations, red is majority color and blue is minority color. But in third, fifth, and sixth combinations, blue is majority color and red is minority color. Now, by looking at the other hats, player can identify whether they are wearing a majority color or a minority color. For instance, if a player sees both a red and blue hat, then the player must be wearing the majority color, which could be red or blue. If a player sees 2 blue or 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here is what players can reason among the 6 choices. If the player is wearing minority color, then he knows that the color, which will be the opposite a color of what the player sees. For example, if a player sees 2 blue or 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in the first combination, if the player C is guessing the hat, now the player sees 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. In the second combination, if the player B is guessing the hat, now the player sees 2 red hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. Similarly, in the third combination, if the player A is guessing the hat, now the player sees 2 blue hats, then the player must be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is red color. So now the idea is to get the player with the minority hat color to guess and force the other people to pass. So here is the strategy. If you see both a red and a blue hat, then pass. If you see 2 red hats, then guess blue. If you see 2 blue hats, then guess red. This strategy wins in all 6 cases with at least one hat of each color. It only loses in the 2 cases of all red or all blue, in which all players guess incorrectly. Here is how players would guess. Here in the first combination, player A sees 2 red hats. Then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color. Since he is wearing red color hat, team will lose. Same happens with player B and player C. Similarly, in the fifth combination where all players wearing blue hats, here also team loses. Here in the combination, player A sees 2 blue hats. Then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is red color. Since he is wearing blue color hat, team will lose. Same happens with player B and player C. So now let's consider the second combination. Here player A see 1 red and 1 blue hat, hence player replies as I pass. Player B again see 1 red and 1 blue hat, hence player replies as I pass. Player C see 2 red hats, then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color and it will matches and team wins. Now let's consider the third combination. In the third combination, player A sees 1 red and 1 blue hat, hence player replies as I pass. Player B see 2 red hats, then the player thinks he will be wearing the minority color, which will be the opposite color of what the player sees. Here in this case, it is blue color and it will matches and team wins. Finally, player C see 1 red and 1 blue hat, hence player replies as I pass. The same logic is applied for other 4 combinations and team wins in all these combinations. So the group wins in 6 of 8 possible outcomes, a whopping 75% chance. So if you follow this strategy, there is a 75% chances of winning the game. This is a little complex puzzle, requires solid strategy in order to solve this problem. You have a torch that takes 2 working batteries. You have 8 batteries, but only 4 of them work. What is the fewest number of pads you need to test to guarantee you can get the torch on? So let me repeat the problem. You have a torch that takes 2 working batteries. You have 8 batteries, but only 4 of them work. What is the fewest number of pads you need to test to guarantee you can get the torch on? So this problem does definitely raise a lot of confusions in the mind about the approach required to solve the problem with the correct answer in fewer number of pads. I will present you the most efficient way to get the correct answer. Pause the video and give it a try before checking the solution, and do not forget to comment if you found something interesting. Let's check the solution. Let's call the batteries as B1, B2, B3, B4, B5, B6, B7 and B8. Torch will work when both the batteries are working. It will not work if any of the battery is faulty. With the best case, if we take 2 pairs of batteries and put them in slot 1 and slot 2, test them out. If working, then fine. Else take another 2 and test them out and continue doing so till you get the correct pair. If you are lucky in these 4 turns, torch will work. But let's say we were most unlucky and it did not work all the 4 times. Also, the whole objective is to find the solution for worst case scenario and not for the best case. Now let's group the batteries in 2 groups of 4. There can be these cases in group of 4. If all 4 batteries are working, then take any pair and we will get working battery in just 1 chance. If only 3 batteries are working, we will get working batteries in max 2 picks. If only 2 batteries are working, scenario becomes tricky because this will open up multiple possibilities and end up in more iteration to find the pair to switch on torch. If only 1 battery is working in the group, then scenario becomes more complex. Hence, grouping batteries in 2 groups with 4 batteries each is not the correct approach. Now I will explain the most efficient way of finding the solution for this puzzle. We know that out of the 8 batteries, only 4 are in working condition. We need 2 good batteries to run. Let's try to divide the 8 batteries in a group of 3, where group 1 and group 2 contains 3 batteries and group 3 contains 2 batteries. By grouping the batteries like this, we are making sure that at least one of the group has 2 working batteries. This is because there are 4 working batteries and only 3 groups present. Going through logic, there must be at least 2 working batteries in any of the groups. Also, by grouping like this, we are reducing the number of combinations required to find the working pair for the battery. So this is the logic for this particular puzzle. So now let's find how many combinations are possible for each group. Let's go one by one. In group 1, which consisting of B1, B2, B3, possible combinations are B1, B2, B2, B3 or B1, B3. Hence total combinations in group 1 is 3. In group 2, B4, B5, B6, possible combinations are B4, B5, B5, B6 or B4, B6. Again, in this particular group, the total combinations possible is 3. Finally, in group 3, B7, B8, possible combinations is only 1. So the total combinations in group 3 is 1. We know that at least one of the groups has 2 working batteries. By logic, any one of these combinations must work. So adding all the combinations in all 3 groups, it will yield 7. Hence, most number of trials needed is 7. So let's summarize. Break the batteries into 3 groups with 2 groups of 3 batteries and 1 group of 2 batteries. By doing this, you are guaranteed that one of the groups has 2 working batteries. Both of the groups of 3 have 3 possible combinations of 2 batteries and the group of 2 only has 1 combination. So 3 plus 3 plus 1, which equals to 7, tries at most to find 2 working batteries. A duck that is being chased by a fox saves itself by sitting at the center of circular pond of radius r. The duck can fly from land but cannot fly from the water. Furthermore, the fox cannot swim. The fox is 4 times faster than the duck, assuming that the duck and fox are perfectly smart. Is it possible for the duck to ever reach the edge of the pond and fly away to its escape from the ground? Let me repeat the puzzle. A duck that is being chased by a fox saves itself by sitting at the center of circular pond of radius r. The duck can fly from land but cannot fly from the water. Furthermore, the fox cannot swim. The fox is 4 times faster than the duck, assuming that the duck and fox are perfectly smart. Is it possible for the duck to ever reach the edge of the pond and fly away to its escape from the ground? Let's check the solution now. This is not a simple mathematical puzzle to solve like normal common problems. Fox in this puzzle is too fast and clever for any normal and simple strategy. One would think that the duck could swim directly away from the fox, so the duck would have to swim a distance r. The fox would have to cover half the circumference of the pond, that is pi r. Pi r because the circumference of a circle is 2 pi r, but here fox has to cover half the circumference, hence distance becomes pi r. But this strategy won't work, since the fox is 4 times faster than the duck. We know that the value of pi is 3.14, thus pi into r. This is the distance which should be covered by the fox, whereas 4 into r is the distance to be covered by duck. But as we know that since the value of pi is 3.14, pi r is less than 4 into r. Hence, in this strategy, by the time duck swims to near the land, fox would have already reached, which puts duck into danger. This would make it seem like it is impossible for the duck to escape, but there is a way to escape. So how could the duck make life more difficult for the fox? If the duck just tries to swim along a radius, the fox could just sit along the radius and the duck would continue to be trapped. Logic is, the duck could swim in concentric circles so that the fox has to continuously run along the circumference of the pond to stay on the same radius as the duck. If the duck swims near the edge of the pond, the fox could easily keep up since they would be covering approximately the same distance and the fox is 4 times faster. But what if the duck swam close to the center of the pond? The duck would have to cover a smaller circumference in this case and could use this strategy to put some distance between the fox and itself. Consider at a distance of r/4 from the center of the pond, the circumference of the pond is exactly 4 times the circumference of the duck's path. Because we have considered the distance is r/4 where r is the radius. Let the duck rotate around the pond in a circle of radius r/4. Now fox and duck will take exact same time to make a full circle because the fox is 4 times the speed of the duck. So at a distance of r/4 from the center of the pond, the circumference of the pond is exactly 4 times the circumference of the duck's path. Thus, to stay on the same radius as the duck, the fox would barely keep up. Now, reduce the radius the duck is circling by a very small amount. Now the fox will lag behind, he cannot stay at a position as well. Say the duck circles the pond at a distance r/4 minus e, where e is an infinitesimal amount. So as the duck continues to swim along this radius, it would slowly gain some distance over the fox. Once the duck is able to gain 180 degrees over the fox, the duck would have to cover a distance of 3r/4 plus e to reach the edge of the pond. So why 3r/4 plus e? This is because the duck is already at the distance r/4 minus e, so the distance what it has to cover to reach the land is 3r/4, which is the remaining distance, plus e, which is an infinitesimal amount. So in the meanwhile, the fox would have to cover half the circumference of the pond, that is the 180 degrees at that point. So here, since pi r, which is a distance to be covered by the fox, is greater than 4 into 3r/4 plus e, which is a distance to be covered by duck in the same time, since pi r, which is distance to be covered by fox, is greater than 4 into 3r/4 plus e, which is a distance to be covered by duck. So as we clearly see that the time taken by a duck to reach the land is greater than the time taken by a fox to reach the duck at that particular point of time. So that's the reason the duck will reach the land and it will fly and escape. So in this way, the duck would be able to make it to land and fly away. A man fell in a 30-meter deep well. In one day, he climbs 4 meters up and slips 3 meters down. How many days would it take for him to come out of the well? Let me repeat the puzzle. A man fell in a 30-meter deep well. In one day, he climbs 4 meters up and slips 3 meters down. So in this case, how many days would it take for him to come out of the well? On first day, man climbs 4 meters up and slips 3 meters down, which means that on first day in total, man climbs only for a meter. Similarly, on second day, man climbs for another 4 meters and slips 3 meters down again, which means that on second day, total distance man climbs is 2 meters. This infers that the man climbs 1 meter in total each day. So like this, on 26th day, you would have climbed 26 meters. The interesting part comes on the 27th day. And on 27th day, he will climb 4 meters again. So on 27th day, man climbs full 30 meters because on 26th day, he already climbed 26 meters. And remember, on 27th day, man will not slip since he is already out of the well. This is the place where many candidates fail to analyze the problem. Many candidates will answer this as 30 days, which is incorrect. Think logically and you can easily solve this problem without any difficulties. Thus, in this puzzle, a man climbs a total of 30 meters in 27 days. He will be out of the well on 27th day. An intelligent trader travels from one place to another carrying 3 sacks having 30 coconuts each. No sack can hold more than 30 coconuts. On the way, he passes through 30 checkpoints, and on each checkpoint, he has to give 1 coconut for each sack carrying. How many coconuts are left in the end? Let me repeat the puzzle. An intelligent trader travels from one place to another carrying 3 sacks having 30 coconuts each. No sack can hold more than 30 coconuts. On the way, he passes through 30 checkpoints, and on each checkpoint, he has to give 1 coconut for each sack carrying. The question is, how many coconuts are left in the end? Let's assume that the maximum capacity of each sack is 30 coconuts. In the first view, most of the people thinks that the answer to this puzzle is 0. If you take all conditions literally, then nothing would be left. But the keyword here is intelligent trader. So you need to think according to an intelligent trader. Being an intelligent trader, he will definitely use all his intelligence to get the profit, that is by trying to save as much coconut as possible. Now I am going to explain step by step how the trader is going to save maximum coconuts possible. Initially, the trader passes through 10 checkpoints, leaving the trader with 20 coconuts per sack. It is because on every checkpoint, the trader has to give 1 coconut from each sack. This means at the end of 10 checkpoints, total left out coconuts in each sack is 20. The trick to save coconuts lies at this point. At this point, what trader does is, he distributes all coconuts from one sack into the other 2 sacks, leaving 2 sacks each filled with 30 coconuts, and 1 sack will be empty at this point. From here, at each checkpoint, trader have to give only 2 coconuts because there are only 2 sacks left. Later, trader passes through 15 more checkpoints. After passing through 15 more checkpoints, the trader now has 15 coconuts per sack, or 30 coconuts in total. At this point, trader will transfer the coconuts into 1 sack. Now the trader is left with 30 coconuts in a sack. From here, at each checkpoint, trader have to give only 1 coconut because there is only 1 sack left. By this point, 25 checkpoints already covered and remaining checkpoints are 5. Now trader will pass through the 5 remaining checkpoints, and if trader spends another 5 coconuts in other 5 checkpoints, the trader is left with 25 coconuts. Thus, answer to this puzzle is the total number of coconuts left in the end is 25. By following these simple steps, you can solve this logical puzzle very easily. A lady got kidnapped by a gangster. The gangster puts 2 bullets in consecutive order in an empty 6-round revolver, spins it, points it at her head and shoots. She is still alive. The gangster then asked her, "Do you want me to spin it again and fire, or pull the trigger again right away. The question is, which option should be preferred? For each option, what is the probability that she will be shot? Let's check the solution now. The most important point here to consider is that the bullets were loaded adjacent to each other. There are 6 ways to arrange the 6-round revolver with consecutive bullets. These are the possible scenarios which can be arranged with the 2 consecutive bullets. But the first shot went blank, and hence the last 2 possibilities are of no use. We can easily eliminate these possibilities. Let me explain this in detail. As per the puzzle, gangster already shot once and it is blank. This implies that in the combinations, first value cannot be B, it must be X, which is empty. Hence the combination starting with B must be eliminated. So now the 4 possible arrangements of the consecutive bullets considering the first blank attempt are these. Now looking at these possibilities, our odds of getting shot are 1 by 4 or 25%. This is the only combination she will get shot. In all other combinations, the immediate one is blank. Since there are 4 combinations, in only one combination she is getting shot, it is 1 by 4 or 25% of the possibilities where she gets shot. If he respins, then following are the combinations. As we can see here, there are 2 possibilities out of 6 combinations where lady will be shot. Looking at these possibilities, our odds of getting shot is 2 by 6 or 33%. So she should prefer pulling the trigger again right away, which is 25% possibility of getting shot, instead of respin, which increases to 33% of getting shot. This is the solution for this puzzle. Think that you have 2 identical ropes, which are non-uniform in composition. Each rope takes 60 minutes to burn, but the ropes are not identical, meaning 90% of the rope may burn in 5 minutes and rest 10% may take 55 minutes or any such composition. You don't have any watch but a lighter. How will you calculate 45 minutes? So I will repeat the puzzle. You have 2 identical ropes which are non-uniform in composition, and each rope takes 60 minutes to burn, but their composition is non-uniform, meaning 90% of the rope may burn in 5 minutes and rest 10% may take 55 minutes, or 80% of the rope may burn in 5 minutes and rest may take 55 minutes, or any such composition. You don't have any watch but a lighter. So the question is, how will you calculate 45 minutes? Let's check the solution now. As it is told in the question, the ropes are non-uniform. It means that if you cut a rope in 2 halves, then both halves may not take 30 minutes each to burn. But on a whole, the rope will take 60 minutes to burn. This approach is not going to help. So in order to calculate 30 minutes, you only need 1 rope. So what you can do is burn the rope from both ends. It will take the rope 30 minutes to burn completely. Even though it is non-uniform, but if you burn on both the sides, it's definitely going to take 30 minutes because the composition does not matter since you are not burning the rope from one side. So in order to calculate 45 minutes, the 1 rope is not sufficient. You need 2 ropes. Let's call the ropes A and B and follow the below process in order to measure 45 minutes. What you have to do first is burn rope A from both ends and rope B from one end. So rope A will completely burn in 30 minutes. So because it is put on fire from both the ends. As we saw in the question itself, the rope takes 60 minutes to burn. Since you are burning on both the sides, the whole rope will burn in 60 minutes. So when rope A is burnt completely, you have already measured 30 minutes. But the rope B would have burnt for 30 minutes. It does not mean that the rope B is off burnt, but it has already taken 30 minutes and the remaining portion of the rope will burn in another 30 minutes. So at this point, lit the other end of rope B as well. It will take another 15 minutes for rope B to burn completely. So that's how you are going to measure 45 minutes. So I will repeat the solution. So what you are supposed to do is first burn rope A from both ends and rope B from one end. So rope A will completely burn in 30 minutes because it is put on fire from both ends. When rope A is burnt completely, rope B would have burnt for 30 minutes. So it does not mean that rope B is off burnt. At this point, lit the other end of rope B as well. It will take another 15 minutes for rope B to burn completely. So that's how you have measured 45 minutes. Once there was a king. The king wanted to protect his kingdom from the outside world. So he made a rule that neither any citizen of the kingdom can go to the outer world nor anyone from outside can enter his kingdom. There was a common bridge between the kingdom and the outside world. The guard was assigned on the gates of the kingdom, which was linked to the bridge. If anyone tried to go out of the kingdom, he or she will be killed. And if anyone tried to come inside the kingdom, the guards would send them back. It takes 8 minutes to cross the bridge. The guard was allowed to take a 5 minutes break. One woman was able to cross the bridge and move to the outside world. How did she do that? Let's check the solution now. As per the puzzle, there is only one common bridge through which anyone can enter to the kingdom or leave from the kingdom. Total time taken to cross the bridge is 8 minutes, and guards are assigned to the bridge to monitor. There is no way to cross the bridge without guards' notice, since total time required to cross the bridge is 8 minutes, but the guard was allowed to take maximum of 5 minutes break. The time when the guard was at rest, if the woman starts to walk towards the outer world, she will be caught after 5 minutes and will be killed. This is because, as per the king's order, if anyone tried to go out of the kingdom, he or she will be killed. And if anyone tried to come inside the kingdom, the guards would send them back. The solution to this puzzle requires out-of-the-box thinking. Let me explain now how women could be able to cross the bridge from the kingdom. The time when the guard was at rest, the woman will start to walk towards the outer world. She will walk for 5 minutes and then will turn back towards the kingdom. Since she had no document with her, she was not allowed to come inside the kingdom. Now guards think that the woman is trying to enter the kingdom. Therefore, the guards sent her outside the kingdom. Hence, she was able to leave the kingdom. So this is how women will make a plan in order to escape from the kingdom. If you have not understood the solution, please do watch again. So the trick is simple. Immediately, the time when the guard was at rest, the woman will start to walk towards the outer world. She will walk for 5 minutes and then will turn back immediately towards the kingdom. When the guards come back, they think that the woman is trying to enter the kingdom, not escaping from the kingdom. Therefore, the guards sent her outside the kingdom instead of killing her. Hence, she was able to leave the kingdom. Suppose we have 3 glasses and 10 coins. The problem is to place odd number of coins in each glass. That is, each glass should contain coins and the number of coins in each glass must be odd and total coins which will be used must be equal to 10. Let me repeat the puzzle. Suppose we have 3 glasses and 10 coins. The problem is to place odd number of coins in each glass. That is, each glass should contain coins and the number of coins in each glass must be odd and total coins which will be used must be equal to 10. This is one of the fantastic puzzle asked in the job interviews. Let's check the solution now. See, it is not possible to use all 10 coins with each glass having odd number of coins. This is because if you add odd number of coins odd number of times, then the result is always odd but not even. But here there are 10 coins which is even. That is the challenge here. There are even number of coins but number of glasses are odd. Therefore, we must think out of the box. Let's solve now logically. So in the first step, in the first glass, place 5 coins which is odd. After that, in the second step, in second glass, place 2 coins. And in the third step, in third glass, place 3 coins which is odd. Here the first glass contains 5 coins which is odd, second glass contains 2 coins which is even, and the third glass contains 3 coins which is odd. Now is the important step. After third step, glass 1 has 5 coins, glass 2 has 2 coins and glass 3 has 3 coins. Now place the entire third glass inside second glass. By doing this, we are making sure that the second glass has 5 coins. Hence indirectly, now second glass contains 5 coins which is odd in nature. Three ants are walking in the same direction. The first ant has 2 ants behind him, the second ant has 1 in front and 1 behind. But the third ant has 1 in front and 1 behind too. How is this possible? Let me explain the solution now. The most widely accepted and logical answer to this riddle is the ants are moving in the same direction but in a circular manner, not in straight line. Let's say the ants are A, B and C. A has B and C behind him, B has A in front and C behind, and C has B in front and A behind. In this way, third ant has 1 in front and 1 behind too. There can be other solution to this riddle. Do share yours in the comment section. But the most widely accepted answer to this riddle is the ants are moving in a circular manner. There are 4 prisoners. All 4 prisoners will be freed if at least one of them correctly guesses the color of the hat on his head. They can't speak to each other and they can't touch each other. However, if they take part and one of them gives a wrong answer or none of them can work out the answer at all, then their sentences will be doubled. They are told that there are 4 hats, 2 white and 2 black. Each man will have a hat placed on his head while blindfolded. When each man is wearing a hat, the blindfolds will be removed. The prisoners will not be able to see their own hats, and the only way they can work out what color hat they are wearing will be from looking at the hats the other prisoners are wearing. All they have to do to win their freedom is for one of them to work out what color hat he is wearing. But there is a twist. To make it more interesting, 3 prisoners stand in a line facing a brick wall. The prisoner at the back, say A, stands on a box and can see both of the prisoners in front of him, say B and C. Prisoner B stands on a smaller box and can only see prisoner C, who in turn can only see the wall. The fourth prisoner D stands on the other side of the wall and can see nothing of the other prisoners nor his own hat. They are not allowed to turn around or converse in any way. There are no mirrors and they all know that there are 2 black hats and 2 white hats and that there are 4 people. The prisoners are told that they have 5 minutes and to call out as soon as one of them thinks he knows for certain what color hat he is wearing. Remember, if just one of them gets the answer wrong, they will all have their sentences doubled. One of the prisoners says, I know the color of my hat, and solves the riddle. Which prisoner is that? The placement of the prisoners in the room is as the following. Can you solve this riddle? Let me explain the solution now. Each one of the prisoners knows that there are 4 hats, 2 black and 2 white. If prisoner A observes that prisoner B and C have the same colored hats, he would assume that he has the opposite color and solve the riddle. However, since prisoner B and C have different colored hats, prisoner A doesn't say anything. After waiting about 4 minutes, prisoner B calls out the right answer. You can see that C is wearing a white hat. If B was wearing a white hat too, then A would have seen 2 white hats and would have known that his hat was black. As A didn't say anything, B knew that he and C must have different color hats on, and as C's hat is white, B knew that his hat must be black. Through this logical approach, prisoner B could able to answer the right hat color, and all 4 prisoners will be freed. As shown in the image, there are 9 dogs within a fence. By constructing just 2 more square fences, can you make sure that each dog is in isolation? Let me repeat the puzzle. As shown in the image, there are 9 dogs within a fence. By constructing just 2 more square fences, can you make sure that each dog is in isolation? Let's check the solution now. It might seem tricky at first, but there is a very simple way of working out the real answer. To solve this riddle, one just needs to draw a diagonal square and a straight square inside it. First, let's draw a diagonal square. Now, draw a straight square. As we can see now, by constructing just 2 square fences, each dog is in isolation. This is one of the most interesting riddle which requires out of the box thinking to achieve the correct answer. Suppose a newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. Suppose that rabbits never die and that the female always produces one new pair, one male and one female, every month from the second month on. How many pairs will there be in 1 year? This is an excellent puzzle. Don't come to conclusion immediately. This requires a proper analysis to find the correct solution. Let me explain the solution now. To begin with, initially there are newly born pair of rabbits. Also, we know that newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month, so that at the end of its second month, a female can produce another pair of rabbits. So at the end of the first month, they mate, but there will be only one pair. It is because rabbits are able to mate at the age of 1 month, so that at the end of its second month only, a female can produce another pair of rabbits. At the end of the second month, the female produces a new pair, so now there are 2 pairs of rabbits in the field. So at the end of the second month, there are 2 pairs. At the end of the third month, the original female produces a second pair, making 3 pairs in all in the field. This is because it is given in the question that rabbits never die and that the female always produces one new pair, that is one male, one female, every month from the second month on. So at the end of the third month, there are 3 pairs. Now at the end of the fourth month, the original female has produced yet another new pair. The female born 2 months ago produces her first pair also, making 5 pairs. So at the end of fourth month, there are 5 pairs. Now at the end of fifth month, the original female has produced yet another new pair. The female born 3 months ago produces her second pair. The female born 2 months ago produces her first pair, making 8 pairs. So at the end of the fifth month, there are 8 pairs. This continues, but the problem is it is difficult to keep the track and solve this problem like this. Let's check, is there a pattern to generalize the solution? So pattern is, initially there is 1 pair, at the end of first month still there is 1 pair, at the end of second month there are 2 pairs, at the end of third month there are 3 pairs, after 4 month there are 5 pairs, after fifth month there are 8 pairs, and this continues. And this is the sequence of numbers which famously called the Fibonacci sequence. In the Fibonacci sequence, the next number is found by adding up the 2 numbers before it. Here is a first 13 Fibonacci numbers. As we can clearly see that here the first 2 numbers are 0 and 1. The next number is found by adding up the 2 numbers. Here the first 2 numbers are 0 and 1. Next number 1 is found by adding the 2 numbers before that. That is 0 plus 1 equals 1. The next number 2 is found by adding the 2 numbers before it. That is 1 plus 1 equals 2. The next number 3 is found by adding the 2 numbers before it, that is 1 plus 2 equals 3. And the next number 5 is found by adding the 2 numbers before it, that is 2 plus 3 equals 5, and this continues. This puzzle follows the Fibonacci sequence starting with 1. Here is the sequence which represents the number of pairs present after 1 year. So as we can clearly see that there are 233 pairs of rabbits present after 1 year with this logic. Thus, answer to this puzzle is 233 pairs of rabbits. There are 233 pairs which will be there in 1 year. For your information, Fibonacci sequence was first discovered by Italian mathematician Fibonacci, also known as Leonardo Bonacci. The original problem that Fibonacci investigated was in the year 1201, and it was about how fast rabbits could breed in ideal circumstances. There are 13 caves arranged in a circle. There is a thief in one of the caves. Each day, the thief can move to any one of the adjacent cave or can stay in the same cave in which he was staying the previous day. And each day, cops are allowed to enter any 2 caves of their choice. What is the minimum number of days to guarantee in which cops can catch the thief? There are 3 important notes that anyone should keep in their mind in order to solve this puzzle. The first note, thief may or may not move to adjacent cave. The second note, cops can check any 2 caves, not necessarily be adjacent. And the final note, if thief and you exchange your caves, you will surely cross at some point and you can catch the thief immediately. Let me explain the solution now. For convenience sake, let's name 13 caves from C1 to C13. Now, let's assume the thief is in cave C1 and going clockwise, and cops start searching from cave C13 and C12 on your first day. So on the next day, cave C13 and C11 on second day, C13 and C10 on third day, and so on till C13 and C1 on 12th day. So basically the aim is to check C13 every day so that if thief tries to go anti-clockwise, you immediately catch it, and if goes clockwise, cops will catch him in maximum 12 days. This includes the case where he remains in cave C1. So the answer to this puzzle is 12. See, there are multiple question arises, and some people believes that this approach is not going to cover all scenarios. One argument is, how does this guarantee that you can catch the thief? What if the thief moves into a cave you have already checked? Suppose on nth day you checked cave 13 and cave 7 when the thief was in cave 6. Next day you would check C13 and C6, whereas the thief moves into C7 so that you won't see him. Or what if thief decided to move into a cave you just checked when you were in the other cave you planned for the day? You can't be checking inside two caves at the same time, right? So this question arises because in most of the plays, people won't provide third note in the puzzle. That leads to confusion. Third note clearly states that if thief and you exchange your caves, you will surely cross at some point and you can catch the thief immediately. According to this note, if the thief moves into a cave you have already checked, the thief will be caught in between. Example, on nth day, you checked cave 13 and cave 7 when the thief was in cave 6. Next day, you would check C13 and C6, whereas the thief moves into C7. But here, thief will be caught while moving from C6 to C7. It is because at the same time, police also will be moving from C7 to C6. So concerns on the logic of the puzzle is addressed. So the most widely accepted answer to this puzzle is 12. Let me read the puzzle now for you. There are 100 people standing in a circle in an order 1 to 100. Number 1 has a sword. He kills the next person, that is number 2, and gives the sword to the next, that is number 3. All people do the same until only one survives. Which number survives at the last? So let me repeat the problem. There are 100 people starting from 1 to 100. One has a sword. He kills the next person, that is number 2, and gives the sword to the next, that is number 3. All people do the same until only one survives. You are supposed to identify which number survives at the last. Let me solve this puzzle more logically. Consider the case where there are 2 to the power of n numbers in the circle. If the total number of people is 2 to the power of n, then each time the number reduces by half and the number 1 remains till the end. For example, if there are 32 people, in the first round, 16 people dies and remaining people will be 16. And in the second round, out of 16 people, 8 people dies and remaining people will be 8. And in the third round, out of 8 people, 4 people dies and remaining people will be 4. And in the fourth round, out of 4 people, 2 people dies and remaining people will be 2. And finally, in the final round, out of 2 people, 1 person dies and the person 1 is the remaining one. Here the most important point to remember is, when there are 2 to the power of n numbers in the circle, each time the number reduces by half and the number 1 remains till the end. Now let's back to the actual problem. Here in this puzzle, there are 100 people. So the logic is to reduce the people to the number where the number is the power of 2. So in the given scenario, number 1 has a sword. He kills next person, that is number 2, and gives sword to next, that is number 3. First person kills the next. So starting from 1, we will remove next person, that is 2. The first person gives word to next, that is 3. That person will also kill next person and this continues. Means in circle we need to start with 1 and remove the every alternate person till 72. All the even people will be removed till 72 and we will be left with 64 people. It is because 1 kills 2, 3 kills 4 and so on till 71 kills 72. So 36 people have been killed till now since every alternate person is killed. Remaining people is 100 minus 36, which is 64. Now 64 people remain in the circle and the 64 is a power of 2. That is 2 to the power of 6 is 64. We know from the prior example that the case when there are 2 to the power of n numbers in the circle, each time the number reduces by half and the number 1 remains till the end. So here in this case, the first guy after 72 will be new number 1 in a circle of 2 to the power of 6. So number 73 will survive. So understand this more logically. The logic is try to reduce the total number of people to the number where the number is power of 2. In this case, we are actually reducing to the number to 64 since 64 is a power of 2, that is 2 to the power of 6, which yields 64. So when the number reduces to 64, as per the prior example, the number 1 always survives. But here we are already reached to the number 72nd. So the immediate first number will be 73rd and the 73rd will be the first number when the people are standing in the circle when the number is reduces to the number which is power of 2. Hence in this case the 73rd person will survive. A bat and a ball cost $1.1 in total. The bat cost $1 more than the ball. How much does the ball cost? Let me repeat the puzzle. A bat and ball cost $1.1 in total. The bat cost $1 more than the ball. How much does the ball cost? Many people think that the ball must cost 10 cents. Although this response automatically comes to mind, but it is incorrect. 10 cents answer is incorrect because if the ball cost 10 cents and the bat cost $1 more than the ball, then the bat would cost $1.1 for a grand total of $1.2. Then what is the correct answer to this particular puzzle? The correct answer to this problem is that the ball cost 5 cents and the bat cost at $1 more, that is $1.05 for a grand total of $1.1. Not convinced? Let me solve this by using algebraic equation. Read the question again. They haven't asked the cost of bat, but they said cost of bat is $1 more than ball. Let x be the value of ball and bat cost $1 more than ball. So now bat costs x plus $1. As per the question, total cost of bat and ball is $1.1. Now equation becomes cost of bat plus cost of ball equals $1.1. The cost of bat is x plus $1 and the cost of ball is x dollars. So the equation becomes x plus 1 plus x equals 1.1. After solving this equation, the equation becomes 2x plus 1 equals 1.1. After solving for x, the value of x comes to 0.05. Thus the cost of ball is 5 cents and the cost of bat is $1.05. So why do so many people answer incorrectly? The answer is that people often substitute difficult problems with simpler ones in order to quickly solve them. In this case, people seem to unconsciously substitute the more than statement in the problem, that is the bat costs $1 more than the ball, with an absolute statement the bat costs $1. So one must be very careful while solving these kind of problems. Best way to think to solve these kind of problems is by using algebraic equations. An Arab sheikh tells his 2 sons to race their camels to a distant city to see who will inherit his fortune. The one whose camel is slower will win. The brothers, after wandering aimlessly for days, ask a wise man for advice. After hearing the advice, they jump on the camels and race as fast as they can to the city. What does the wise man say? So let me repeat the puzzle. An Arab sheikh tells his two sons to race their camels to a distant city to see who will inherit his fortune. The one whose camel is slower will win. The brothers, after wandering aimlessly for days, ask a wise man for advice. After hearing the advice, they jump on the camels and race as fast as they can to the city. So let's check the solution now. The wise man tells them to switch camels. Let's check how this will work. Each son owns a camel. Let's call them Camel A and Camel B. If Camel A is slower, son A gets the fortune. If Camel B is slower, son B gets the fortune. Neither of the sons wants to enter the city first because they won't get the fortune. When they switch camels, son A is now riding his brother's camel, Camel B, and son B is riding his brother's camel, Camel A. Now they each want the camel they are riding to get to the city first. If son A wins the race on Camel B, that means his camel, that is Camel A, was slower and he wins the fortune. The same is true for the other way around if the second son wins the race on Camel A. Thus, the suggestion given by the wise man is tell them to switch the camels so that the task will be completed soon. The riddle states that in a square room there is a cat in every corner. There are 3 cats in front of each cat. The riddle asks the total number of cats present inside the square room. Let's check the solution now. There are multiple solutions for this riddle depending on the interpretation. If you read that there are 4 cats in the room and in front of each cat is another 3 cats, then it might lead you to the answer of 16. This is not correct. You will have reached this answer if you assumed that there was 3 cats in front of every cat in the corner. That would mean 4 cats in every corner, which is 4 into 4 equals 16. This is incorrect answer. Let's understand the riddle properly to achieve the correct solution. From the first statement, in a square room there is a cat in every corner. It is clear that there is a square room with a cat in each corner of the room. Since a square room has 4 corners, the total number of cats present in the room is 4. The next line states that there are 3 cats in front of each cat. We know that there are 4 cats in the corners of the room. When we apply the second statement to this scenario, it is clear that every single cat in the room has 3 cats in front of it. Thus, one solution to this riddle is 4, and most of the people think this is the right solution. Going through this interpretation, the answer is 4. Let me explain now the different interpretation. The total number of cats in this square room will be in the range of 4 to infinity. Let's break this riddle down. In each corner of a square room is a sitting cat. A square room has 4 corners, 1 cat per corner, so 4 cats so far. In front of each cat there are 3 cats. An important but missing piece of information is which way each cat from each corner is facing. If the 4 cats are all facing each other, then each cat is facing 3 cats from the other corners. Therefore, there are still 4 cats in total. But if any one of the 4 cats turns and faces their respective corner, then there will be infinite cats. This is to meet the condition that each cat faces 3 cats. It is a result of recursion without a terminating condition. Thus, in this approach, the answer is ranging from 4 to infinity. A farmer challenges an engineer, a physicist, and a mathematician to build him a fence that encloses the most area with the least amount of fencing. The engineer makes a circular fence claiming that it is the most efficient. The physicist made a long straight line of fence and said the length was infinite, as fencing of the world was the most efficient way. The mathematician laughed at the others and then proceeded to build the winning fence. What did he build? Let me repeat the riddle. Listen carefully. A farmer challenges an engineer, a physicist, and a mathematician to build him a fence that encloses the most area with the least amount of fencing. The engineer makes a circular fence, claiming that it is most efficient. The physicist made a long straight line of fence and said the length was infinite, as fencing off the world was the most efficient way. The mathematician laughed at the others and then proceeded to build the winning fence. What did he build? Let me explain the solution now. Remember, this is a riddle in the traditional sense. Try to think outside the box. The solution is the mathematician builds a small circular fence around himself and declares himself on the outside. This is the most important point. Just after building a small circular fence around himself, he declares himself on the outside. In this way, mathematician built a fence to the whole world just by using minimal fencing. He is only one outside the fence. You are on your way to visit your grandma, who lives at the end of the valley. It's her anniversary and you want to give her the cakes you have made. Between your house and her house, you have to cross 5 bridges, and as it goes in the land of make-believe, there is a troll under every bridge. Each troll quite rightly insists that you pay a troll toll. Before you can cross their bridge, you have to give them half of the cakes you are carrying, but as they are kind trolls, they each give you back a single cake. How many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 2 cakes? Let me repeat the puzzle. You are on your way to visit your grandma, who lives at the end of the valley. It's her anniversary and you want to give her the cakes you have made. Between your house and her house, you have to cross 5 bridges, and as it goes in the land of make-believe, there is a troll under every bridge. Before you can cross their bridge, you have to give them half of the cakes you are carrying, but as they are kind trolls, they each give you back a single cake. How many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 2 cakes? Answer to this puzzle is 2 cakes. At each toll bridge, you are required to give half of your cakes and you receive 1 back, which leaves you with 2 cakes after every bridge. Let's analyze the solution. In the first toll, you give 1 cake to troll because we are assuming that you started journey with 2 cakes and in each toll, you have to give half of the cakes. In this case, it is 1. In return, you receive 1 cake back, hence there is no loss to you. You started with 2 cakes. After first toll, you still having 2 cakes and this will repeat in all remaining tolls. So if you start with 2 cakes, you will end up with 2 cakes after the last toll. Thus, answer to this puzzle is 2. This is a very simple scenario. What if the question is asked in such a way that there are only 3 bridges and how many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 3 cakes? This requires generalized solution. Let's assume you are carrying X cakes. Since you have to give half of the cakes you are carrying and each give you back a single cake, the number of cakes after first bridge is X divided by 2 plus 1, and after solving this equation becomes X plus 2 divided by 2. After second bridge, number of cakes left is X plus 2 divided by 2 whole divided by 2 plus 1. After solving this equation becomes X plus 6 divided by 4. So after third bridge, number of cakes left is X plus 6 divided by 4, which is actually the total number of cakes remaining after the second toll, divided by 2 plus 1. After solving, equation becomes X plus 14 divided by 8. And we know that the number of cakes left after third bridge is 3. Solve this equation for 3. After solving, we get the X value is equal to 10. So thus, if there are only 3 bridges and number of cakes you have to leave home with to make sure that you arrive at grandmas with exactly 3 cakes is 10 cakes. This is generalized solution. You can use this technique for any number of cakes. There is an old riddle about a lily pad in a pond. The lily pad doubles in size every day, and after 30 days it completely covers the pond. On what day does the lily pad covers off the pond? Let me read the riddle. The lily pad doubles in size every day, and after 30 days it completely covers the pond. On what day does the lily pad cover off the pond? Let me explain the solution now. Remember, this is a riddle in the traditional sense. Try to think outside the box. If you answered without really thinking about it, you probably answered day 15. Our mind automatically goes to this answer because we are comfortable with linear thinking. If the lily pad covers the entire pond in 30 days, then it must cover off the pond in 15 days is what most of the people thinks. Of course, if you stopped to think about it, you would realize that the lily pad only covers off the pond on day 29th. It then doubles one final time and covers the entire pond on day 30. Hence, the solution to this particular riddle is day 29. A more interesting question is, how much of the pond would the lily pad have covered on day 15? Take a second and write down an estimate. Comment your answer in the comment section. The correct answer is that the lily pad will only have covered 0.0031% of the pond on day 15th. That is 3,000ths of 1%. In fact, the lily pad will only cover more than 1% of the pond on day 24th. What makes this riddle difficult is that the lily pad's growth is exponential, not linear. Our minds are comfortable with linear growth. Linear growth is easy to envision, and we are fairly good at estimating things that grow linearly. However, we struggle to envision exponential growth, and our estimating skills often fails us. There are between 50 and 60 eggs in a basket. When he counts by threes, there are 2 eggs left over. When he counts by fives, there are 4 eggs left over. How many eggs are there in the basket? This problem can be solved by conveniently dividing the problem into 3 statements. In statement 1, given that the total number of eggs in the basket are between 50 and 60. Let's say number of eggs equals E. So based on first statement, number of eggs will be in between 50 and 60. In statement 2, it is also given that if counted 3 eggs at a time, 2 eggs are left over. So number of eggs E will be a multiple of 3 between 50 and 60 plus 2. That is, remainder should be 2 after dividing number of eggs present in the basket by 3. So multiple of 3 between 50 and 60 are 51, 54, 57. Possible answers for E based on statement 2 are 53, 56, 59. Here we have added 2 for the multiple of 3 between 50 and 60. In statement 3, it is also given that if counted 5 eggs at a time, 4 eggs are left over. So number of eggs E will be a multiple of 5 between 50 and 60 plus 4. That is, remainder should be 4 after dividing number of eggs present in the basket by 5. So multiple of 5 between 50 and 60 is 55. Possible answers for E based on statement 3 is 59. So the common value for E based on statement 2 and 3 is 59. Thus number of eggs in the basket is 59. In a new hotel containing 100 rooms, Tom was hired to paint the numbers from 1 to 100 on the doors. How many times will Tom have to paint the number 8? Essentially, the puzzle is asking you to determine how many 8s are there between 1 and 100. Here 1 is supposed to find out how many 8s are there from 1 to 100. So you have to go through the numbers and make a note of every one which contains 8. Let me explain the solution now. Answer to this riddle is 20. Let me elaborate how we get the answer 20. Singling them out, the total number of 8s between 1 and 100 are as follows. While there may only be 19 numbers in total, it's easy to forget when determining your answer that the number 88 of course contains not 1 8 but 2 8. And this is one of the most important point you must remember while solving these kind of riddles. If you want to find the answer in the mind without writing, you can follow this simple step. Consider A be a 2-digit number, and if you keep first digit as 8, there are 10 ways of filling B, that is from 0 to 9. If you keep second digit as 8, there are 10 ways of filling A, that is from 0 to 9. So he needs to write 8 10 times in 1's place and 10 times in 10's place, which will result in 20 combinations. Thus the answer to this particular riddle is 20. A man has 53 socks in his drawer, 21 identical blue, 15 identical black and 17 identical red. The lights are out and he is completely in the dark. How many socks must he take out to make 100% certain he has at least one pair of black socks? So let's check the solution now. The answer to this puzzle is 40 socks. If he takes out 38 socks, adding the two biggest amounts, that is 21 and 17, although it is very unlikely, it is possible they could all be blue and red. To make 100% certain that he also has a pair of black socks, he must take out a further 2 socks, which results in 40 socks. By doing so, he will make sure that he will get at least one pair of black socks. In the given figure, the person in box 13 is in his office. He wants to visit every other person in all other rooms before he goes out. The only condition is that he doesn't visit or enter the room of any person twice. Let me repeat the puzzle. The person in box 13 is in his office. He wants to visit every other person in all other rooms before he goes out. The only condition is that he doesn't visit or enter the room of any other person twice. This puzzle seems complicated to many people who attempted to solve it. However, this riddle requires you to focus on minute details before approaching the solution. Let's check the solution now. While many people try to crack this puzzle, most of the people they visited a chamber twice. There is a trick to find the solution for this puzzle. The trick is one has to enter room 14 and then come back to 13. If you know this particular trick, this puzzle is simple. After the first step, he has to proceed from 13 and then towards 9. From 9, he will enter 11 and then towards 15 and 16. The person has to visit 12 from 16 and then to 8. After this, he will move to 7, 6 and 5 before entering 1. Then from 1, he will proceed to 2, 3 and take an exit from room 4. Remember, this is the trick to solve this puzzle. If Teresa's daughter is my daughter's mother, what am I to Teresa? I will repeat the riddle. If Teresa's daughter is my daughter's mother, what am I to Teresa? The options are grandmother, mother, daughter, granddaughter. I am Teresa. So there is an easy way to work out the answer, and that method involves taking out some of the steps in the riddle. Let's check the solution now. If you have already figured out the answer, then it's great. If you are struggling, let me explain the solution now. It might seem tricky at first, but there is a very simple way of working out the real answer. My daughter's mother is much more complicated way of saying me or my female partner. Once you have worked that out, now the riddle is Teresa's daughter is me or my partner. Alright, say there are two possibilities here. First, I is a male, second, I is a female. If you take the first case into consideration, Teresa's daughter equals my daughter's mother, or Teresa's daughter equals my wife. Hence, I here is Teresa's son-in-law. Now if you take the second case into consideration, Teresa's daughter equals my daughter's mother, or Teresa's daughter equals me, because definitely if I am a female, then I am my daughter's mom. Hence, I here is Teresa's daughter. So we get two answers here, that is, one is son-in-law. The answer is son-in-law when I is a male. Otherwise, the answer is daughter when I is a female. Therefore, you are either Teresa's daughter or son-in-law, and since son-in-law isn't an option, you are Teresa's daughter. There is an island of puzzles where numbers 1 to 9 want to cross the river. There is a single boat that can take numbers from one side to the other. However, maximum 3 numbers can go at a time, and of course, the boat cannot sail on its own, so one number must come back after reaching to another side. Also, there is a condition which states that the sum of numbers crossing at a time must be a square number. For example, 1, 2, and 3 cannot cross the river because sum of these numbers is 6, which is not square of any number 1 to 9. You need to plan trips such that minimum trips are needed. What is the minimum number of trips required for numbers 1 to 9 to cross the river? Let me explain the solution now. Answer to this puzzle is we need only 7 trips to send all digits across the river. Let me elaborate the solution now. According to the puzzle, the sum of numbers crossing at a time must be a square number. The important thing to remember is maximum number that can be obtained using any 3 numbers with a range 1 to 9 is 24. That is by using 7, 8 and 9. So sum of 3 numbers must be 1 or 4 or 9 or 16. We can eliminate 1 and 4 because no 3 numbers add up to 1 or 4. The minimum number possible adding 3 numbers is 6, that is by using 1, 2 and 3. The correct square number that can be used to achieve the solution to this puzzle is 16, which is a square of number 4. So this is how we can achieve. In the first trip, send 2, 5, 9. Sum of these numbers is 16, which is a square of number 4. While coming back, bring back the number 9, which is a second trip. In the third trip, send 3, 4, 9, and again sum of these numbers is 16, which is a square of number 4. While coming back, bring back the number 9, which is a fourth trip. In the fifth trip, send 1, 7, 8. Sum of these numbers is again 16, which is a square of number 4. While coming back, bring back the number 1, which is a sixth trip. Finally, in seventh trip, send 1, 6, 9. Again, sum of these numbers is 16, which is a square of number 4. As we can see now, number 1 to 9 have crossed the river in only 7 trips. There can be other patterns which can be a solution to this puzzle. Do share your pattern in the comment section. A prisoner is faced with a decision where he must open one of two doors. Behind each door is either a lady or a tiger. They may be both tigers, both ladies, or one of each. If the prisoner opens a door to find a lady, he will marry her, and if he opens a door to find a tiger, he will be eaten alive. Of course, the prisoner would prefer to be married than eaten alive. Each of the doors has a statement written on it. The statement on door 1 says, in this room there is a lady, and in the other room there is a tiger. The statement on door 2 says, in one of these rooms there is a lady, and in one of these rooms there is a tiger. The prisoner is informed that one of the statements is true and one is false. Which door should the prisoner open? Let me explain the solution now. As per the puzzle, each of the doors has a statement written on it. The statement on door 1 says, in this room there is a lady, and in the other room there is a tiger. The statement on door 2 says, in one of these rooms there is a lady, and in one of these rooms there is a tiger. Let's analyze the statements now. For a moment, let's assume that first statement is true. That is, the lady is behind the door 1 and tiger is behind the door 2. But this makes statement 2 also true, where it says there is tiger behind one of these doors and lady behind one of these doors. Hence, the statement 1 can't be true. Hence, statement 2 must be true. As per the second statement, only possibilities left are: first possibility, door 1 tiger, door 2 tiger. Second possibility, door 1 lady, door 2 lady. And the third possibility is door 1 tiger, door 2 lady. As per the second statement, in one of these rooms there is a lady, and in one of these rooms there is a tiger. Since the true second statement is suggesting there is lady behind one door and tiger behind the other door, the possibilities of both tigers or ladies are eliminated. The only remaining option is door 1 tiger and door 2 lady. That's why behind door 1 is tiger and behind door 2 is lady. Thus prisoner must open door 2 for survival. There are 100 doors in a row. All doors are initially closed. A person walks through all doors multiple times and toggle, which means if door is open, then close. If door is closed, then open. Person does this in following way. In first walk, the person toggles every door, that is first, second, third, fourth till 100th door. In second walk, the person toggles every second door, that is second, fourth, sixth, eighth, so on till 100th door. In third walk, the person toggles every third door, that is third, sixth, ninth, 12th, so on till 99th door. In other words, person toggles all doors which are multiple of 3. If person performs these operations, you are supposed to find which doors are open in the end. According to the problem statement, in first walk, the person toggles every door, that is first, second, third, fourth till 100th door. Hence, after the first walk, every door is open. In second walk, the person toggles every second door, that is second, fourth, sixth, eighth, so on till 100th door. Hence, on the second walk, person only visits the even doors. So at the end of second walk, the even doors are closed and the odd ones are opened. In third walk, the person toggles every third door, that is 3rd, 6th, 9th, 12th, so on till 99th door. In the third time, person will close door 3, opened from the first pass, open door 6, closed from the second pass, and person will close door 9, opened from the first pass, open door 12, closed from the second pass, and it repeats. A door is toggled in nth walk if n divides door number. For example, consider the door number 45. So 45 door is toggled in 1st, 3rd, 5th, 9th, 15th and 45th walk because these are the numbers which divides 45. So the door is switched back to initial stage for every pair of divisors. For example, 45 is toggled 6 times for 3 pairs, that is 1, 45, 3, 15 and 5, 9. So on walk 1, person will open the door. In walk 3, he will close it. Walk 5, he will open it. Walk 9, he will close it. Walk 15, he will open it. Walk 45, he will close it. So for every pair of divisors, the door will just end up back in its initial state, that is in the closed state. So let's consider one more example. Say door 42. Person will visit it for every divisor it has. So 42 has 1 and 42, 2 and 21, 3 and 14, 6 and 7. So on pass 1, person will open the door. On pass 2, he will close it. Pass 3, he will open it. Pass 6, he will close it. Pass 7, he will open it. Pass 14, he will close it. Pass 21, he will open it, and pass 42, he will close it. So for every pair of divisors, the door will just end up back in the initial state. So it looks like all doors would become closed at the end. But there are door numbers which would become open. Example, door 9. So 9 has the divisors 1 and 9, 3 and 3. But 3 is repeated because 9 is the perfect square. So you will only visit door 9 on pass 1, 3 and 9, leaving it open at the end. Only perfect square doors will be open at the end. You have 240 barrels of wine, one of which has been poisoned. After drinking the poisoned wine, one dies within 24 hours. You have 5 slaves whom you are willing to sacrifice in order to determine which barrel contains the poisoned wine. How do you achieve this in 48 hours? Let me repeat the puzzle again. You have 240 barrels of wine, one of which has been poisoned. After drinking the poisoned wine, one dies within 24 hours. You have 5 slaves whom you are willing to sacrifice in order to determine which barrel contains the poisoned wine. How do you achieve this in 48 hours? Let's check the solution now. The number system we generally use is base 10 or decimal system. A number can be represented in multiple ways such as base 10, base 2, base 8. Similarly, a number can also be represented in base 3 system. Base 3 uses only 0, 1 and 2 to represent any number. If you are not familiar, this is easy. Binary system uses 0 and 1 to represent the number, whereas ternary system uses 0, 1 and 2 to represent the number. Though conversion techniques remain same for binary and ternary systems. Now let's use the base 3 system in order to solve this puzzle. Let the barrels be numbered from 1 to 240, and this is represented in base 10. And the same number can be represented in base 3 from 0, 0, 0, 0, 1 till 2, 2, 2, 2, 0. Here the first number represents number 1, whereas second number represents 240. Hence there are 3 digits in ternary system corresponding to 3 outcomes in the given problem for each slave. Let's assign the digits to the outcomes. When it is 0, the slave does not die. When 1, the slave dies within the first 24 hours. When 2, the slave dies in the last 24 hours. So now arrange 5 slaves and let's give the wine from each barrel to the slaves. Convert each number associated with the barrel to its equivalent base 3 representation, which will be 5-digit number. Now consider example. Assume for barrel 139. Here barrel number is 139, which is represented in base 10, and its equivalent base 3 representation is 1, 2, 0, 1, 1. You can use online calculator or any other calculation methods to convert the number from base 10 to base 3 representation. Here, if you observe carefully, third digit is 0, so don't feed slave 3 from this barrel. The logic is simple. So in this case, third digit is 0, so don't feed slave 3 from this barrel. First, fourth and fifth digits are 1, so feed slave number 1, 4 and 5 from this barrel at time t is equal to 0. Second digit is 2, so feed slave 2 from this barrel at time t is equal to 24. So if slave 1, 4 and 5 dies at first 24th hour and slave 2 dies at 48th hour, then barrel 139 is poisonous. Now the problem has become more simple. Let's consider one more example. Now I am considering the barrel number 231. Here barrel number is 231, which is represented in base 10, and in equivalent base 3 representation it is 2, 2, 1, 2, 0. Here fifth digit is 0, so don't feed slave 5 from this barrel. Third digit is 1, so feed slave number 3 from this barrel at time t is equal to 0. And the first, second and fourth digits are 2, so feed slave number 1, 2 and 4 from this barrel at time t is equal to 24. If slave 3 dies at first 24th hour and slave 1, 2 and 4 dies at 48th hour, then barrel 231 is poisonous. So with these simple steps, we can find which barrel is poisonous based on which slaves die. To make the concepts clear, let's consider one more example. If slave number 2 and 4 die in the first 24 hours and slave 3 dies in the next 24 hours, then the barrel number can be represented like 0, 1, 2, 1, 0, which is base 3 representation. And its equivalent base 10 representation is 48. Hence, in this case, barrel 48 is poisonous. By following these simple steps, you can find which barrel is poisonous. On a circle, there are 2014 light bulbs, 2 are on and 2012 are off. You can choose any bulb and change the neighbor state from on to off or from off to on. Doing so, can we get all 2014 light bulbs on? If yes, how? So let me repeat the puzzle. On a circle, there are 2014 light bulbs. 2002 are on state and remaining 2012 are in off state. You can choose any bulb and change the neighbor state from on to off or from off to on. Remember, if you select any bulb, you can change the state of the neighboring bulbs only. Doing so, can we get all 2014 light bulbs on? If yes, how? Pause the video and give a try before checking the solution, and do not forget to comment the answer in the comment section. Let's check the solution now. This puzzle is a perfect example which requires out-of-box thinking. Most of the students or candidates give up solving this problem, and most of the time they end up answering unrealistic answers for the puzzle. If you think that it is not possible to get all 2014 light bulbs on, then you are wrong. Yes, it is possible to get all 2014 light bulbs on. Let's look at the most logical way of solving this kind of puzzles. For the convenience, label 2014 bulbs from B1 to B2014. First and foremost, the most important point is the position of the light bulbs, which is on state is not given. So we assume that they are adjacent and make sure that you are naming the bulbs from here. This is the logic you must remember for this puzzle. That is, the two light bulbs which is in on state, which is mentioned in the puzzle, their positions are not given. So what we do is we assume that they are adjacent, and we will make sure that when we are naming the bulbs, we are starting from this particular point. So example like this. We will start naming the bulbs from the bulbs which are in on state. For example, here B1 and B2 will be in the on state. From B3 till B2014, they will be in the off state. Also, it is given in the question, that is, they are placed in a circular path. Now, since 2 bulb is in on state and remaining 2012 bulbs are in off state, clearly all 2012 bulbs which is in off state are adjacent. Now we will operate on these 2012 bulbs like this. Create a group of 4 off bulbs. We can choose any off bulb apart from the one next to on bulb and able to make 2 bulb adjacent to it in on state. Now choose the third bulb which we just turn in on state and make 2 more bulbs in on state. So clearly we can make 4 adjacent bulbs in on state. Let's understand with an example. First, create a group of 4 bulbs with B3, B4, B5, B6. Remember, B1, B2 are already in on state. At starting, all 4 bulbs are in off state. First, choose second bulb in the group and turn neighboring bulbs 1 and 3 in on state. This looks like this. Now choose third bulb and turn neighboring bulbs 2 and 4 in on state. By doing this, all 4 bulbs are in on state. Once this is done, consider another group adjacent to group 1 and call it group 2 with B7, B8, B9, B10 bulbs. At starting, as we know, all 4 bulbs are in off state. First, choose second bulb in the group 2 and turn neighboring bulbs 1 and 3 in on state, and this looks like this. Now choose third bulb and turn neighboring bulbs 2 and 4 in on state. By doing this, all 4 bulbs are in on state in group 2 as well. By repeating these steps, we can turn all 2012 bulbs into on state. Since there are 2012 bulbs, we have to create 503 groups. 503 is because 4 into 503, which will be resulting in 2012. And by repeating the above steps which I have already discussed, we can turn all 2012 bulbs in on state. A building has 100 floors. One of the floors is the highest floor an egg can be dropped from without breaking. If an egg is dropped from above that floor, it will break. If it is dropped from that floor or below, it will be completely undamaged and you can drop the egg again. There are 2 eggs given. Find the highest floor an egg can be dropped from without breaking, with as few drops as possible. So let me repeat the puzzle. A building has 100 floors. One of the floors is the highest floor an egg can be dropped from without breaking. If an egg is dropped from above that floor, it will break. If it dropped from that floor or below, it will be completely undamaged and you can drop the egg again. So there are two eggs given and you are supposed to find the highest floor an egg can be dropped from without breaking. And the important task is you have to find it with as few drops as possible. Let me explain the solution now. We can assume the eggs break at the same floor and what we are looking for is the next floor down. Our highest non-breaking floor Bn. We can also assume once an egg is broken, it's gone forever. Some solutions are pretty simple. If you don't care about how many tries it takes, you can just start dropping eggs on floor 1 and go up until you have reached the correct floor. Floor by floor would get it done, but in our worst case scenario, the egg breaks at floor 100. This means that linearly, our worst case is 100 drops to find our nth floor. To simplify, this is called brute force logic. In this approach, start from ground floor and keep going up until the egg breaks at floor X. Solution is very inefficient in case the egg doesn't break till the 99th floor. Remember, you need to minimize the number of drops in the worst case. The next approach will be binary search approach. My first thought is that we can immediately rule out binary search because we only have the 2x. With a binary search strategy, we would start with floor 50 and drop the egg from the 50th floor. If the egg breaks, we know our n is below 50. If it's intact, the floor we want is above 50. Suppose the egg breaks. The problem here is now we have lost an egg and only narrowed down our search by 50 numbers. The next step would normally be to split that 50 again and dropping the egg at floor 25th. But if it breaks, we still haven't found our floor. If it doesn't, we have only delayed the inevitable by one more step. And still no solution. The worst case scenario, we have to drop our eggs 50 times. So anyway, this binary search is not going to help in this case. Next approach will be divide a little, conquer a bit. The next solution takes a little bit of the linear approach and mixes in a little of the splitting from our binary approach. We can start off by dropping an egg at floor 10, increasing the drop floor by 10 at a time. Then going back to drop one floor at a time until we find that n. So according to this approach, start from the 10th floor and go up to floors in multiples of 10. If our egg breaks at floor 10, we know n is one of the 9 floors below us. If first egg breaks, say at 20th floor, then you can check all the floors between 11th and 19th with the second egg to see which floor it will not break. If first egg breaks at 30th floor, then you can check all the floors between 21st and 29th with the second egg to see which floor it will not break. In this case, the worst case number of drops is 19. If the threshold was 99th floor, then you would have to drop the first egg 10 times and the second egg 9 times in linear fashion. Seems relatively straightforward, but we can still improve our number of drops. So in this approach, worst case, the egg drops and doesn't break until floor 100, that is 10 drops, and we drop the second egg but don't break it for floors 91 to 99. It brings our worst case drop count to 19 drops. So this is improvised solution but not the best solution. So now let's get into the best solution. The next approach can reduce our worst case scenarios by balancing the linear drops and our 10 floor drop increment. If getting to the higher floors means more drops overall, we need to decrease the drops, we need to perform linearly. We are essentially trying to make all possible scenarios and take the same number of drops to solve. We need to minimize this worst case number of drops. For that, we need to generalize the problem to have n floors. What would be the step value for the first egg? Would it still be 10? Suppose we have 200 floors, would the step value be still 10? So let's understand this in detail. The point to note here is that We are trying to minimize the worst case number of drops which happens if the threshold is at the highest floors. So our steps should be of some value which reduces the number of drops of the first egg. Let's assume we take some step value x initially if every subsequent step is x minus 1. If we drop our first egg from floor x, 10 in our 10 floor strategy, the linear portion of our strategy is x minus 1, that is 9 in the above strategy. So our drop count is x plus x minus 1. If the egg doesn't break on the first drop, our drop count increases by 1. So we will need to remove a drop from our floor to floor drop count. The next drop should be from x minus 1 floors up. Every additional floor jump will need to have one less floor, so that when we get the linear portion of the solution, we will have one less floor to check. We continue removing one floor until we only have one floor to check. So the expression becomes x plus x minus 1 plus x minus 2 plus x minus 3 till plus 1. So this is nothing but the sum of n natural numbers, and it can be calculated using the formula x times x plus 1 divided by 2. Because there are 100 floors in our problem, we solve for x when the entire summation is equal to 100. Now solve for x. When the number of floors are different, we have to evaluate the expression for the different value. So in this case, x times x plus 1 divided by 2 equals 100. So after solving this equation, we get x equals 13.651. This means we want to start dropping from floor 14, jump up 13 floors to drop from floor 27, jump up 12 floors to drop from floor 39, and so on. So our worst case scenario is then a drop count total of 14. Let me explain this in detail. So follow the following sequence. First, drop from floor 14. If it breaks, sequentially check previous 13 floors. Maximum drops required here is 14. Else drop from floor 27 because 14 plus 13 equals 27. This is by the logic x plus x minus 1 plus x minus 2. So we are decreasing one floor in every step. So if it breaks sequentially, check previous 12 floors, that is from 26th to 15th floors. Else drop from floor 39 because 27 plus 12 equals 39. If breaks, check previous 11. Else drop from floor 50 because 39 plus 11 equals 50. If breaks, check previous 10. Else drop from floor 60. If breaks, checks previous 9. Else drop from floor 69. If breaks, checks previous 8. Else drop from floor 77. If breaks, check previous 7. Else drop from floor 84. If breaks, check previous 6. Else drop from floor 90. If breaks, check previous 5. Else drop from floor 95. If breaks, check previous 4. Else drop from floor 99. If breaks, check previous 3. Else 100 is the answer. So the total number of steps required in this case is 14. And this is the most optimal solution for this particular problem. There are 5 pirates A, B, C, D and E. They have a strict hierarchy. A is senior to B, B is senior to C, C is senior to D and D is senior to E. So it is like A's age is greater than B, B's age is greater than C, C's age is greater than D and D's age is greater than E. And this hierarchy is very strict. These pirates have 1000 gold coins which they want to distribute among themselves. The rules of distribution is as follows. The most senior pirate proposes a distribution of coins. The pirates, including the proposer, then vote on whether to accept this distribution, which means all the pirates, including the most senior, will vote on whether they accept the proposed distribution or not. If the majority accepts the plan, the coins are distributed and the game ends, which implies that if half or more pirates vote in the favor of distribution, then proposed distribution is accepted and game ends there. If more than half pirates votes against the distribution, then the senior most pirate will be killed and the next senior most will propose a new distribution, and this will continue. The process repeats until a plan is accepted or if there is one pirate left. In case of a tie vote, the proposer has the casting vote. The casting vote is a vote that someone may exercise to resolve a deadlock. So these are distribution rules, and there are some rules followed by pirate also. And these are the rules every pirate follows. First of all, each pirate want to survive. The second, given survival, each pirate want to maximize the number of gold coins he gets. Third, given a situation of no gain, no loss, each pirate would prefer to kill the other pirate. Considering that all pirates are very strong in logic, and if a logic can be deduced, then they will deduce it. The problem statement is, how should pirate A distribute the coins so that it does not get killed and also gets the maximum coins possible? So I will repeat, how should A distribute, that is the most senior pirate will distribute the coins so that it does not get killed and also gets the maximum coins possible. Take your time to solve this puzzle before checking the solution. Let's check the solution now. Naturally, it may appear that A will have to give most of the coins, if not all, to the junior pirates so that his life can be saved. But that will not work because every pirate wants to maximize coins. Suppose if A decide to distribute 250 coins to each B, C, D and E and keeps nothing for himself to get saved, then also E will be killed because all others will vote against him. They can get the same distribution even if A is killed and pirates want other pirates to be killed. This is because the next senior pirate may think that he will get more coins compared to the current distribution, hence disagrees. Similar thought process goes with every pirate, and hence everyone disagrees with the logic because every pirate wants to maximize number of coins. So finding a solution like this is very difficult. The solution to such puzzles can be easily found working in the bottom-up approach. Let's go step by step. Suppose if number of pirate is 1. That is, if there is just one pirate, say E, then the distribution is very easy. E keeps everything to himself. This is the most ideal scenario. Number 2, suppose if there are 2 pirates, say D and E, D is senior to E. Then the distribution strategy should be done by D. D will distribute the coins like this. Pirate D can easily propose that he gets all the 1000 gold coins. Since he constitutes 50% of the pirates, because there are only 2 pirates in this scenario, the proposal has to be accepted, leaving Pirate E with nothing. So Pirate E knows now he gets nothing if there are only 2 pirates are left. In this case, D will vote in favor of his distribution and the distribution will be accepted because of people voted in favor it. So in this scenario, D gets everything and E gets nothing. Number 3. Suppose if there are 3 pirates, C, D and E, C being senior most, then C will make the following distribution. According to this distribution, C gets 999 coins, D gets 0 coin and E gets 1 coin. See, if there are 3 pirates, Pirate C needs one other person to vote for his plan. The trick to this puzzle is understanding that if Pirate C's plan is voted down, he would die and then there would be only 2 pirates on the boat. We already figured out what happened when there are only 2 pirates on the boat. In the case of 2 pirates, Pirate E receives nothing. So Pirate C can simply offer Pirate E a single gold coin and ensure his vote. As a perfectly rational pirate knows 1 coin is better than no coins at all. So now C will obviously vote in favor. He knows that if C dies, then D will make the next distribution and he will get nothing. Hence, E will also vote in favor because they want to maximize their profit. And the distribution is accepted because more than 50% is voted in favor, that is 2 votes is compared to 1 vote. So number 4, suppose if there are 4 pirates, say B, C, D, E. B being senior most, B will make the following distribution. According to the distribution, B gets 999 coins, C gets 0 coin, D gets 1 coin and E gets 0 coin. If there were 4 pirates, Pirate B needs to convince one other person to guarantee 50% of the vote. He could give Pirate E 2 gold coins, but his greed makes him realize that if his plan is destroyed, there will only be 3 pirates on the board. When there are 3 pirates left, Pirate D knows he will get nothing. So Pirate B buys Pirate D's vote with 1 gold coin. Now B and D will vote in favor of this distribution because if the distribution is not accepted and B dies, then C will have to make the distribution and D will get nothing. You can see the distribution when there are 3 pirates. Hence, because 50% pirates voted in favor of distribution, it will be accepted. Finally, if there are 5 pirates, A, B, C, D and E. A being the senior, A will make the following distribution. According to the distribution, A gets 998 coins, B and D gets 0 coin, C and E gets 1 coin. When there are 5 pirates, Pirate E needs 2 other associates. He realizes that if he dies, Pirate C and Pirate E will get 0 coin. So he offers each of them 1 gold coin and makes off with the other 998 gold coins. By the same logic, A, C and E will vote in favor of distribution and hence the distribution will be accepted. So this is the final distribution logic made by A. This is how A distributes the coins so that he does not get killed and also gets the maximum coins possible. See, this question can be tweaked to confuse. If you know the logic, then any tweaks to the original puzzle can be analyzed in the right direction. Now if the question is asked for 6 pirates, then you can answer similarly. In fact, we can find the solution for any number of pirates. In the same puzzle, suppose if there are 100 coins and 15 pirates, how does the most senior pirate save his life and gets as much coins for himself as possible? Let me explain now. So for a larger number, a pattern looks like this, and let's analyze the pattern. If there were only 1 pirate, he would keep all the gold for himself. I have already explained the logic in the prior section. If you have not understood it, you can watch it again. If there were 2 junior most pirates, the senior one would keep all the gold for himself and his junior would have to agree because the senior's vote would make 50% of the vote as discussed earlier. If there were 3 pirates, then the senior most of these, the third pirate, gets to make the decision. He knows that if he is killed, the junior most would get nothing. So he gives 1 coin to him and gets his vote to make more than 50% vote. That is, he keeps 99 for himself and gives 0 to the second one and gives 1 coin for the first one. For 4 pirates case, 4th pirate knows the situation earlier. That is, for 3 pirate case, he knows that the best junior most writer can get 1 coin and the best second pirate can get is 0 coins. So if he gives just 1 coin to the second pirate, then the second one would always agree. So he keeps 99 for himself, gives 0 to third and first pirate and 1 coin to the second pirate. This gets him 50% votes and he wins. So now coming to the 5th pirate. So he has his own vote on whatever decision he makes, of course, and needs 2 more votes. He knows that in case of his death, first and third would get nothing. So he buys their vote by offering 1 coin each and keeps 98 for himself. Which means that to get the 50% votes, the senior most pirate needs to give n-1 divided by 2 coins to his juniors, where n is number of pirates. So 15th pirate would get 100 minus 15 minus 1 divided by 2, which equals to 100 minus 7 is equal to 93 coins. And from the pattern, 14th pirate would not get any coin. 13, 11, 9, 7, 5, 3 and first pirate would get 1 coin each. So this is how we have to identify the number of coins each will get for this kind of puzzles. If the question is tweaked in any ways and if you know the logic, you can answer this puzzle without any confusion. Let's look into one more difficult puzzle. Even though the logic required is same, but it is little bit tricky, so watch it very carefully. So this is 6 pirates fight for 1 gold coin. So here is the puzzle details. 6 pirates discover a chest containing 1 gold coin. They decide to sit down and devise a distribution strategy. The pirates are ranked based on their experience. Pirate 1 to Pirate 6, where Pirate 6 is the most experienced. The most experienced pirate gets to propose a plan and then all the pirates vote on it. If at least half of the pirates agree on the plan, the gold is split according to the proposal. If not, the most experienced pirate is thrown off the ship and the process continues with the remaining pirates until a proposal is accepted. The first priority of the pirates is to stay alive and second to maximize the gold they get. Pirate 6 devises a plan which he knows will keep him alive. What is his plan? So let's understand the solution. The question is more complex version of 5 pirates fight for 1000 gold coins. If you have not read through question, please do so. I'm going to explain the solution assuming you know the other solution. If there is only one pirate, he takes the coin. If there are 2 pirates, Pirate 2 takes the coin, leaving Pirate 1 with nothing. In both the scenario, it constitutes more than 50%. If there are 3 pirates, Pirate 3 needs 1 more vote. There is no way we can convince Pirate 2 since he benefits if Pirate 3 dies. Pirate 3 gives the gold coin to Pirate 1 to give his vote, so he survives. If there are 4 pirates, Pirate 4 needs 1 more vote. He can't give it to Pirate 1 since Pirate 1 will get the gold coin even if Pirate 4 dies. He can give it to either to Pirate 2 or 3, which will get him another vote to ensure his survival. If there are 5 pirates, Pirate 5 needs 2 more votes. There is no way he can get 2 more votes since there is only 1 gold coin to bribe with. Pirate 5 dies regardless of his approval. You can think about it. So think about the scenario and there are 5 pirates. So Pirate 5 cannot make any kind of a plan in order to survive. With any approach, he will not get more than 50% vote. Anyway, he is going to die if there are 5 pirates left. So if there are 6 pirates, Pirate 6 needs 2 more votes. He will surely get Pirate 5's vote since Pirate 5 will die if Pirate 6 dies. If Pirate 6 and Pirate 5 die, Pirate 4 will survive but will not get the gold coin. So Pirate 6 can bribe Pirate 4 with a gold coin and gets his vote. That makes a total of 3 votes allowing Pirate 6 to survive. He can also give the gold coin to Pirate 1, 2 or 3. Although giving it to Pirate 2 or 3 is a little confusing since either of them could get the gold coin in the case of 4 pirates. So this is how we have to think when solving this kind of puzzle. If you have understood the logic, if these kind of puzzles are asked in any different ways, you should be in a position to answer it. This is how your approach should be. You have to go from top-down approach so that you can actually deduce the logic in order to solve this kind of puzzles. You are standing before 2 closed doors. One of the doors leads to heaven and the other one leads to hell. 2 watchmen are standing, one in front of each door. You know one of them always tells the truth and the other always lies. But you don't know which watchman tells the truth and who is the liar. You can ask only one question to one of them in order to find the way to heaven. What will you ask? This is one of the most interesting puzzles and asked in several job interviews. Feel free to pause the video and try yourself before checking the solution. Let's check the solution now. The solution to this puzzle is, you should go to any one of the watchmen and ask him, if I ask the other watchman about which side leads to heaven, what would he answer? If you ask a direct question, which door leads to heaven, then the honest one will tell the truth and the liar watchman will point toward the door that leads to hell. But here we are not asking the direct question, we are asking one watchman about how the other will answer. Let me explain how this particular solution holds good for this situation. If you ask the honest watchman how the other, that is liar, will answer, he knows that the liar will point towards hell. So he will tell you that the answer will be the hell's door. If you ask the liar watchman how the other, that is honest, will answer, he knows that the honest one will point towards heaven door. But since he is a liar himself, he will tell you the other door, which is the door of hell. Hence, in both the cases, irrespective of whether the watchman is honest or liar, he is pointing to the hell's door. So you can choose the other path to continue your journey to heaven. Thus, instead of asking direct question, you can achieve the solution by asking indirect questions to watchmen. One person has some money in his pocket. He visits 4 temples on the way. As soon as he visits any temple, the money in his pocket gets doubled, and on his way out, he donates ₹100 to each temple. In total, he visits 4 temples. After visiting the last temple, his pocket is empty of all the money. So how much money he had initially? So let me simplify the puzzle. One person has some money in his pocket. He visits 4 temples on the way. As soon as he enters a temple, his money gets doubled and he offers ₹100 in each temple. Thus his pocket gets empty after he returns from the 4th temple. Now the question is, how much money he had initially? So let's check the solution now. Let's assume a person began his quest with ₹X. So what exactly happens in first temple is, as soon as he enters the temple, his money is doubled to 2x. On his way out, he donates ₹100. Therefore, he is left with ₹2x minus 100. So 2x because the money got doubled and the 100 because he donates to the temple. So in second temple, as soon as he enters the temple, his money is doubled to 2 into 2x minus 100. 2x minus 100 is the money left before visiting the second temple. So on his way out, he donates another ₹100 and he is left out with ₹4x minus 300. This we will get after solving the equation 2 into 2x minus 100 minus 100. In third temple, as soon as he enters the temple, his money is doubled to 2 into 4x minus 300. 4x minus 300 is the money left before visiting the third temple. On his way out, he donates another ₹100 and he is left with ₹8x minus 700.
So in fourth temple, as soon as he enters the temple, his money is again doubled to 2 into 8x minus 700. We already know that 8x minus 700 is the money left before visiting the fourth temple. On his way out, he donates another rupees 100 and he is left with rupees 16x minus 1500. According to the question, after his last visit, he completely runs out of money. Therefore, the equation is 16x minus 1500, which is the money left after the visit of fourth temple, equals to 0, because according to the question, after his last visit, he completely runs out of money. After solving this equation becomes x equals 1500 divided by 16, hence x is equal to 93.75. Hence a person had started his quest with rupees 93.75 in his pocket.
A certain town comprises of 100 married couples. Everyone in the town lives by following rule. If a husband cheats on his wife, the husband is executed as soon as his wife finds out about him. All the women in the town only gossip about the husbands of other women. No woman ever tells another woman if her husband is cheating on her. So every woman in the town knows about all the cheating husbands in the town except her own. Husbands always remain silent. One day, the mayor of the town announces to the whole town that there is at least one cheating husband in the town. In this situation, what do you think happens? So I will simplify the puzzle. A certain town has 100 married couples, husband and wife only. Everyone in the town lives by the following rule. If a husband cheats on his wife, the husband is executed, that is killed, as soon as his wife finds out about him. Husband may enjoy only as long as his wife does not get to know about it. All the women in the town only gossip about the husbands of other women, but no woman ever tells another woman if her husband is cheating on her. So every woman in the town knows about the cheating husband in the town except her own. And husbands always remain silent. So one day, the mayor of the town announces to the whole town that there is at least one cheating husband in the town. So in this situation, what do you think happens? Let's check the solution now. Let's solve this puzzle methodically. Say there was only one cheating husband in the town. So this is the first condition that I am considering. That is, there was only one cheating husband in the town. So in this situation, there will be 99 women who know exactly who the cheater is. The one remaining woman who is being cheated on would have assumed there is no cheaters. But now that the mayor has confirmed that there is at least one cheater, and she realizes that her own husband must be cheating on her. So her husband gets executed on the day of the announcement. So this is what happens if there is only one cheating husband in the town. But what mayor actually announced is there is at least one cheating husband in the town. So now let's assume there are two cheaters in the town. So in this condition, there will be 98 women in the town who knows who the two cheaters are. The two wives who are being cheated on would think that there is only one cheater in the town. Since neither of these two women know that their husbands are cheaters, they both do not report their husbands in on the day of announcement. The next day, when the two women see that no husband was executed, they realize that there could only be one explanation: both their husbands are cheaters. Thus, on the second day, two husbands are executed. Through induction, it can be proved that when this logic is applied to n cheating husbands, they all die on the nth day after the mayor's announcement.
So let's simplify the solution of this puzzle. So let's start methodically and consider different cases. So consider the case 1. If there is only one cheating husband. In this case, 99 women knows who is cheating. Only one woman, wife of the cheater, does not know of anyone cheating. Wife of the cheater must be thinking that none of the husbands cheat. After announcement, she will realize that her own husband is cheating, because if anyone else is cheating, then she must have been aware of it. So the cheating husband will die on the first day. So consider the case 2. If there are two cheating husbands, the wives of both the cheating husbands think that there is only one cheating husband, that is the other one, and hence will expect the other husband to die on the first day. When no one dies on the first day, then on the second day, both of them will realize that their husband is also cheating along with the other one. Hence, both the cheating husbands die on the second day. Think about like if there are n cheating husbands. Going by this logic, they all die on the nth day after the mayor's announcement. you.